I'm Nicky Fox, project scientist for Parker Solar Probe, and this is Solar 60. I'm here at Astrotech's Space Operations Clean Room, and with me is Marco Velli, the observatory scientist for Parker Solar Probe. Marco, can you tell us, why are we sending this mission to journey so close to the Sun?
Well, Nicky, the Sun's outer atmosphere, or corona, rises to a temperature of about 3 million degrees, powered by the Sun's magnetic field, which stores enormous amounts of energy, and then releases this energy in bursts, equivalent to several million hydrogen bombs every day. This continual release of energy leads to the supersonic expansion of this corona into space, which we call the solar wind. This blustery solar wind is created by complex heating processes that we simply do not yet understand. The only way to grasp how all this works is to finally explore the Sun's corona, where all the exciting physics is taking place.
And what does this mean to you personally to be involved in such a groundbreaking mission?
For me, this mission has been a journey. I grew up in the 60s when space exploration was in its infancy, and one of the first discoveries was just how powerful the magnetic activity of our star can be. When I started working in physics, I was studying how energy and magnetic fields could produce useful nuclear fusion on Earth, but I was soon drawn to the astrophysics of the Sun. When I read about the idea of a solar probe, I was determined to work on the mission, and I have done so for over 25 years. We have so many ideas, and yet we know we will find unexpected surprises. I can't wait for what Parker Solar Probe will reveal.
Thanks, Marco. I really think everybody following this mission is thinking the same thing. That's it from the clean room at Astrotech. I'm Nicky Fox, and this is Solar 60.
ESIS, the Integrated Science Investigation of the Sun, is an experiment which looks at energetic particles over a broad range of energies, from tens of thousands of electron volts up to about 100 million electron volts. The ESIS instrument is based on solid-state detectors. Those are detectors that when a particle passes through them, energy is deposited, and you can measure that energy, and you can measure that the particle has actually passed through. So there's the solar wind, which is this continuous flow of lower energy particles. And then there are much more sporadic and episodic events like solar flares that spew out great numbers of these much more energetic particles. In our higher energy instrument, we have a whole set of layers of these detectors. And when a particle passes through those layers, it leaves energy in each and every one of those detectors. Those detectors are also segmented in pieces like a pie. And so when a particle comes through from a particular direction, you can tell both the direction the particle came through at, and you can tell the energy and species of that particle by looking at all the different energy depositions. In our lower energy instrument, we also have the same sort of solid-state detectors, but in addition to that, we use an extra trick, which is when a particle passes through a very thin foil, it ejects an electron. We're able to detect that, and that gives us the start timing for the particles. One of the big issues for ESIS is to understand the difference between solar energetic particles that just come from the Sun with a certain energy and those that are energized in interplanetary space as they move outward. By the time they get out to the Earth's orbit, that's all so messed up, mangled up, that it's kind of hard to tell the difference between those. But as we get in closer and closer to the Sun, we'll be able to differentiate those two types of sources, which will be really important for understanding the fundamentals of energetic particles in the solar system. By going in close and measuring the detailed distributions of these energetic particles, their energies, directions, and their species, we're going to learn things that we couldn't possibly learn by looking forever from a remote distance. And by understanding our Sun in detail, we can understand lots of other stars in much greater detail.
Hi, I'm NASA Kennedy's Mark Shug, and I'm taking you inside KSC. NASA's Parker Solar Probe is being processed for its mission to study the Sun. The probe is being tested and prepared inside the Astrotech Processing Facility near Kennedy Space Center. Engineers and technicians deployed the probe's solar arrays, the main source of power, to check their functionality. Then, with the lights out, we used a laser to illuminate the solar cells to ensure they are working to produce electricity. They also extended and checked the motion of the magnetometer boom to make sure that the insulation blanketing does not bind or interfere with its operation. Parker Solar Probe will launch no earlier than August 4th on a United Launch Alliance Delta IV Heavy rocket from Space Launch Complex 37 at Cape Canaveral Air Force Station. The probe will perform the closest ever observations of a star when it travels through the sun's atmosphere, called the corona. The probe will rely on measurements and imaging to revolutionize our understanding of the corona and the Sun-Earth connection. And remember, Spaceport Magazine digs deeper inside KSC.
Fields is in a special place on the spacecraft. The electronics package is inside the spacecraft where most of the electronics are, but all of our sensors are mounted on the outside of the spacecraft. We have 3 sensors that measure magnetic fields that are mounted on a boom behind the spacecraft in the shadow shield, and then we have 5 sensors that measure plasma voltage. These are electric field sensors. They extend into full sunlight and they get very hot. 2 of the key measurements to understanding coronal heating are the measurement of the magnetic field and the electric field. And together they give us what's called the Poynting flux, which is the energy flux of the corona. And to make those measurements, we have to actually go into that plasma and put sensors in the plasma to measure magnetic fields and electric fields directly, and that's what fields will do. Solar wind is the escaping atmosphere of the sun. It's the escaping corona of the sun. The corona is heated in a way that we don't understand yet, presumably involving magnetic fields, by energy that comes from below in the photosphere, and it's heated to such a high temperature that it can escape the gravitational potential of the sun and become an escaping wind, a stellar wind, a solar wind. Well, the design of the Fields instrument is a new thing for solar wind physics. It kind of combines 2 previous styles of experimentation. There are 2 ways to measure electric fields in space. One is using a technique that's called a double probe. Then there's another technique which is measuring plasma waves or radio waves. And Fields for the first time brings these 2 techniques together. I think the very first data that we get will be revolutionary. At first blush, it'll just be a bunch of numbers as a function of time. But the science team will take those numbers and make visualizations in the form of spectrograms, and eventually those data will be related to models, and so we'll be able to compare directly 3D visual models of the coronal magnetic field. These measurements have never been made in the environment close to the sun. We've made measurements similar to this in the Earth's magnetosphere, Earth's ionosphere, but putting a package like this into the solar corona has just never been done. The closest anyone's ever been to the sun, and based on what we've seen so far from spacecraft not quite as close, it's going to be striking and I think revolutionary.
I'm Evan Smith, and this is Solar 60. We're here at the Astrotech Space Operations Control Room, where Parker Solar Probe is undergoing fault management testing. With me is Sanai Kubota, Parker Solar Probe's fault management lead. Sanai, why do we perform fault management testing on the spacecraft?
Evan, I think you should have asked that question a long time ago. The reason Evan should know this answer is because he is in charge of the testing for the fault management system. He's the one who has made sure that all of our tests are set up to really put the spacecraft through its paces. Because Parker Solar Probe is going so close to the sun, the spacecraft needs to be able to fix itself within seconds if something goes wrong on board in order to keep the spacecraft safe. Fault management testing confirms that the spacecraft makes the correct autonomous decisions. Today we're performing a low battery state of charge fault management test. The problem that we're simulating today is that the battery is draining. We need to switch in new hardware, including a new control computer, and we need to do that quickly enough that we don't start pointing in the wrong direction or overheat any part of the spacecraft. While the spacecraft is working to fix the issue, all components that are not vital to keeping the spacecraft alive are powered off. Unfortunately, even though this is an important science collection time, this includes the instruments. So we also need to make sure that the instruments are powered back on as soon as possible after the reconfiguration is complete. This is the test that confirms that the spacecraft can figure this situation out and do the right thing.
Thanks, Sanai. And that's...
Wait, Evan, who's that on your shoulder?
Sanai, you know who's on my shoulder. This is Dalai Lama, our good luck charm and mascot. That's it from the control room at Astrotech. I'm Evan Smith, and this is Solar 60.
NASA's Parker Solar Probe is a mission to explore the sun. How can it do that? Why won't the spacecraft melt? Excellent questions. You can't face off with the sun without packing the right gear. This is why Solar Probe is equipped with a white shield that reflects heat off the front and keeps things cool in the back.
The heat shield is made out of a couple of different materials. One is carbon-carbon, which is a lot like the graphite epoxy you might see in your golf clubs or your tennis racket, but it's just been superheated. The inside is a carbon foam, which is just another form of carbon and is actually about 97% air. It's a very lightweight way of making a very strong structure.
Nobody likes a needy explorer. Solar Probe can take care of itself, thank you very much. And that's because it has autonomy software that will keep its instruments safe and cool behind the heat shield.
We're too far away to joystick it into place, so it basically has to always be sensing whether or not the heat shield is in the right position and correct itself if it isn't. There are these things called solar limb sensors that are just poking out at the very edge of the shadow. And if those get illuminated, the spacecraft knows, oh, I'm going the wrong direction, and can actually right itself.
It's important to stay hydrated in the sun, even for a spacecraft. Solar Probe circulates water to keep the solar cells from overheating. It stays cool and keeps power.
So basically, water flows behind the solar rays and into the radiators, and so the water warms up when it's behind the solar cells and then cools down up at the radiators, and so that heat transfer is happening a lot like the veins in your body.
Yes, you read right. Heat is not the same as temperature. Temperature is a measurement, but heat is energy transfer. This matters because Solar Probe will be visiting the sun's outer layer, the corona. Like all stars, the sun is made of plasma. How tightly packed that plasma is depends on the layer. While the sun's corona has a very high temperature, the plasma particles are fairly spread out. So even though the temperature in the corona is 2 to 3 million degrees Fahrenheit, the heat around the spacecraft is manageable.
The corona and where we're going is actually not that dense at all. There are only a couple particles. And so when we think about it, those are very hot, but we're not touching a lot of them. It's the kind of like when you put your hand into an oven, and the oven might be at 400 or 500 degrees Fahrenheit, but your hand isn't at 400 or 500 degrees Fahrenheit.
Thanks to its design and destination, this cool, confident spacecraft is all set to explore. We can just sit back and chill as Parker's Solar Probe takes the heat.
Hello and welcome. I am Karen Fox and I'm here at NASA's Kennedy Space Center in Florida to talk about NASA's newest mission, Parker Solar Probe. This is a mission to touch the sun. We are going to be flying through a part of the solar atmosphere called the corona, which reaches millions of degrees in temperature. It is going to be experiencing radiation and heat temperatures that are brutal. But as we go through it, we are going to have our first ever close-up look at a star. This is a particularly auspicious day to be talking about this. Today is July 20th. This is the 49th anniversary of the first time a human stepped foot on the moon. NASA has continued exploring ever since, and here we are talking about going to the sun as well. We have a few speakers here. Today in the room, we are going to have Alex Young. He is a solar scientist from NASA's Goddard Space Flight Center in Greenbelt, Maryland. We have Nicky Fox, no relation, even though we have the same last name. Nicky Fox, Parker Solar Probe project scientist from the Johns Hopkins University Applied Physics Lab. We also have Betsy Congdon. She is also from the Applied Physics Lab, and she is the lead for the thermal protection shield. That is the heat shield. We have an example of it here. We're going to be doing a demonstration with that a little bit later. We will take questions after the speakers have gone. We will also be taking questions from the phone, and we will be taking questions via social media. You can use the hashtag AskNASA, and we will be taking those questions for you. With no further ado, Alex Young will start us off.
Thank you, Karen. So hi, I am Alex Young. I'm the Associate Director for Science in the Heliophysics Science Division at NASA Goddard, and I'm also a solar astrophysicist. And what I want to talk about today are the fundamental science questions that are driving the Parker Solar Probe mission. So if you could put up the first video, please. So the sun is incredibly dynamic. It's always changing, always in motion. It goes through periods of incredible violence and relatively calm periods, but it's incredibly dynamic star. And like other stars, the sun has an ocean of particles and radiation which are flowing out of it, and they're dominated by its magnetic field. And this constant flow of energy and material, something we call the solar wind, permeates the entire solar system. And the extent of the solar wind and the sun is from the sun all the way to the edge of what we define as the solar system. And the space in between is created. So one of the things that NASA is very concerned about is understanding this environment, to characterize this environment, because this is our regime. This is where we live. In fact, we have technology, we have people in space, and we have to understand and characterize this place that we're traveling through. The solar wind is something that is one of the fundamental things we want to understand, one of the fundamental questions that we're trying to address here today. And this is, why is the solar wind so fast? The solar wind goes from sort of a steady breeze to an actual supersonic flow from the corona, going to millions of miles an hour. So why does this happen? What is going on here? Now, in 1958, Eugene Parker wrote a seminal paper describing why the solar wind does this, explaining the solar wind and explaining why it goes from a subsonic to a supersonic flow. And this research is fundamental to how we understand the atmospheres of stars, and in particular how we understand the atmosphere of our sun. But we don't just have the wind, the sun also has storms. In particular, the sun can blast out these huge blobs of material, billions of tons of solar atmosphere threaded with solar magnetic field, traveling away from the sun at millions of miles an hour. And so we want to understand why this happens in the corona and take this data to further improve our models so that we can better predict this, what we call space weather. And this space weather has direct influence not always positive on our technology in space, our spacecraft, can disrupt our communications. It creates a hazardous environment for astronauts. And in the most extreme case of these space weather events, it can actually affect our power grids here on the Earth. So it's of fundamental importance for us to be able to predict the space weather much like we predict weather here on Earth, terrestrial weather. So those are sort of two fundamental questions: the speed of the solar wind, this space weather, explosive space weather storms. But the last question that we're interested in understanding is the corona itself. It's a very strange, unfamiliar environment for us. We're used to the idea that if I am standing next to a campfire and I walk away from it, it gets cooler. But this is not what happens on the sun. As we go from the surface of the sun, which is 10,000 degrees, and quickly move up into the corona, we find ourselves quickly at millions of degrees. So this is a fundamental question that drives not only how this star works, our sun, but actually all the stars in the universe. How does these atmosphere work? And so these are sort of the three fundamental questions we want to address here today: the speed of the solar wind, this eruptive phenomena, solar storms, and how is the corona heated? Thank you.
Thank you so much, Alex. Now that we have some sense of why NASA wants to study the sun and study the space environment, we are going to move on to talking to Nicky Fox. She is the project scientist for Parker Solar Probe, which is scheduled to launch on August 6th, right here from Kennedy.
Thank you very much, Karen. Yes, as Karen said, I have the great honor of being the project scientist for this amazing mission. Alex just did a lovely job of really highlighting why we need this mission so much and why we're so excited as a science community to be finally flying it. These questions: why is the corona about 300 times hotter than the surface of the sun? Why does this coronal atmosphere, that atmosphere that you probably all saw last year during the total solar eclipse, why is this suddenly accelerated and moving away? In 1958, as Alex noted, a seminal paper written by Dr. Gene Parker from the University of Chicago predicted all of this stuff. It is no coincidence that the mission we are talking about today is Parker Solar Probe. Last year, we renamed the mission for Gene Parker. It was the first time that NASA has ever named a mission after somebody during their own lifetime. And we're extremely excited not only to bear his name, but also we're looking forward and anticipating him joining us here at Kennedy Space Center in a couple of weeks when we launch this mission. And so the science is groundbreaking, it's compelling, it's confused scientists and puzzled us for decades and decades and decades. We're now going to fly this mission. So let's sort of dive into how we're going to do it. So we will launch, as Karen just said, August 6th from Slick 37 on a very beautiful United Launch Alliance Delta IV Heavy. If you have a chance to go see it, it is a beast of a rocket. On top of that, we actually have a final stage, a third stage that's going to kick us even more so when we get out into space. We need to go so fast because we have to lose the influence of the Earth. The Earth is traveling around the sun very happily. We do not want to travel around with the Earth. We want to be able to go in towards the sun and really fly through that corona. So we will launch just 6 weeks after our launch. We will encounter the planet Venus for the first time, as this animation will show. Venus is very important to us. 6 weeks, it's a very busy time for us, but we actually use Venus to do gravity assists. Now, not like those other missions you've heard about that, take energy from the planet to speed up. We actually generously give energy to Venus, and we use Venus to slow us down just a little bit, really to focus our orbit, almost like doing a little handbrake turn and focusing us in towards the sun. We will do 24 sort of petal orbits, as this animation shows. coming very close to the sun on one side, going out around the orbit of Venus on the other. I mentioned Venus is very important for us. We will encounter Venus another 6 times during our 7-year mission, allowing us to walk closer and closer into the sun until at our closest approach, we are just 3.83 million miles above the sun's surface. And a lot of people don't think that sounds particularly close, but if I put the sun and the Earth in the end zones on a football field, Parker Solar Probe will be on the 4-yard line in the red zone knocking on the door for a touchdown. So we're very close. There is also a model in the press office here that shows exactly where Solar Probe will be sitting relative to those coronal field lines. Very, very close. Also very fast. At our closest approach, we will be traveling at 430,000 miles an hour, or about 118 miles a second. So fastest human-made object also. We need to go to the corona because we have done so much science by looking at the spacecraft, at the star. We've looked at it in every single different way you can imagine, every wavelength. We've traveled in beyond the orbit of Mercury even, but we need to get into this action region, into the region where all of these mysteries are really occurring. And that's why we are doing this incredibly daring journey, if you like, through the corona 24 times. We are very happy that we are well protected. We have a full suite of instruments to make the measurements that are so key and important for us to be able to close the science that Alex has talked about. So we have instruments that measure all of the magnetic and electric fields. They're looking for plasma waves, the very high energy particles, and we also have a white light imager that is taking pictures basically of what we're about to plow through. And so we have a full suite of instruments. We are nicely protected by our heat shield. Karen already alluded to, and Betsy's going to give you a demonstration in a minute. But if we look at this nice animation, you'll see Parker Solar Probe with the heat shield facing towards the sun and protecting the bulk of the spacecraft from the solar wind. Most of the instruments sit on the main body of the spacecraft. You can see it, the sort of silver structure at the back there, and they are well in the shadow provided by that amazing heat shield. There are a couple of instruments that brave the solar atmosphere. I think of them as very brave little instruments. They peep out around the side, and they have to be in that full environment. And you're going to see a video in a minute from Patrick Hill actually showing you all these things on the spacecraft, so you'll get a good feeling for where these instruments are. Not only do we have a heat shield, we use solar panels, solar power, to really run our mission. That may sound like a no-brainer. Hey, Nicky, you're going to the sun. Big deal. But of course, solar cells need to stay cool. They don't like to overheat, and if they do, they don't work. And so we had to find a way of being able to cool our panels as we are making these cuts through the corona. One final thing for the big technology is she is the most independent. I like to think of her as an independent spacecraft, but she's highly, highly autonomous. She has to look after herself when she's in this coronal region. There is no person in the loop. She is fully capable of figuring out if there's an anomaly, how to rectify it. It takes light 8 minutes to get from the sun to the Earth. We don't have time for her to send a signal, somebody to think about it and send it back. She has to be able to look after herself. And so these are kind of the big technology leaps that we've had to make. That is why we've had to wait 60 years for this mission. And so I'm happy to say that after waiting this long, we are now at the finish line and ready to launch our mission, join all the other wonderful missions that NASA has. Looking at the sun, we're going to be providing that last piece of the puzzle. And so in just a few weeks, we will go and touch the sun.
Fantastic. Thank you, Nicky, so much. We had a chance here to talk about the science, a little bit about what Parker Solar Probe is going to be doing. We next want to tell you all about the spacecraft itself, the kind of things that are on there, and how it will be working. To do that, we have Patrick Hill on a video. He is the Deputy Project Manager for Parker Solar Probe from APL, and you can roll that video. Thank you.
Hi, I'm Patrick Hill, Deputy Project Manager for NASA's Parker Solar Probe. I'd like to take you on a tour of the pioneering spacecraft designed, built, and soon to be operated by the Johns Hopkins Applied Physics Laboratory. In just a couple of weeks, a Delta IV Heavy launch vehicle will rocket Parker Solar Probe out of Earth's atmosphere and begin its long-awaited mission to touch the sun. There are three main technologies on Parker Solar Probe that make this mission possible. They all play an integral part in keeping the spacecraft and instruments safe, healthy, and operating at peak performance. The Thermal Protection System, or TPS, is an essential technology that enables Parker Solar Probe to get so close to the sun. During closest approach, the sun-facing side of the TPS will see temperatures around 2,500 degrees Fahrenheit. Meanwhile, the spacecraft itself will be closer to room temperature, around 85 degrees Fahrenheit. Everything hides behind the shadow or umbra of the TPS, except for a few brave instruments: the field's electrical wave antennas and the Sweep Solar Probe Cup, both of which have their own heat shields. Like many spacecraft, Parker Solar Probe is powered by solar arrays. There are two on each side of the spacecraft, currently hidden beneath their protective covers. What's different about our solar arrays is they must operate within the final 5% of the distance between the Earth and the Sun. That's too much energy for conventionally designed solar-powered systems. The first thing we do is use the actuator motors to move the solar arrays behind the umbra of the TPS, such that only the leading edges are exposed to the sun. That small amount of illuminated surface produces enough energy to power the spacecraft and all of the instruments. The spacecraft uses an innovative cooling system that circulates water throughout both arrays. The heated water is then transported to these large radiators hidden behind the TPS, which then radiates that heat out to deep space. Parker Solar Probe is the first spacecraft to use an actively water-cooled solar array system. During solar encounters, the sun itself blocks Parker Solar Probe from receiving commands from the Earth, and it must rely on its own autonomous systems to keep the spacecraft and science instruments safe. We've placed solar limb sensors all over the spacecraft to determine when it's receiving too much sunlight. Autonomy then determines how best to position the spacecraft by sending commands to the reaction wheels, which adjust the probe's position in space. Parker Solar Probe is one of the most autonomous spacecraft ever designed. Parker Solar Probe culminates the work of tens of thousands of people at NASA, APL, and our partners all over the country and all over the world. It's been an honor to work with such a deeply dedicated and knowledgeable team of scientists, engineers, and technicians. I can only wonder what we'll discover along our mission to touch the sun.
All right, we will be answering questions in just a moment. Remember, if you are on social media, you can use hashtag #AskNASA for that. We have one more demonstration in this room. Before that, we have Betsy Congdon to come up. She is the lead for the thermal protection system, this heat shield right here.
Hi, I am Betsy Congdon. I work at the Johns Hopkins University Applied Physics Lab, and I am the lead engineer for the heat shield, also referred to as the Thermal Protection System, or TPS, for Parker Solar Probe. And I'm going to do a little demonstration here of the heat shield material. What I have next to me is a slice of the heat shield that you saw. We lovingly refer to the heat shield as our 8-foot frisbee because it is about 8 feet in diameter, 4.5 inches thick, but only about 160 pounds. And Nicky talked about how fast we had to go, and everything on this spacecraft really had to be lightweighted in order to achieve those mission objectives. So I'm going to get started here, getting this hot.
I'm going to bring up a volunteer from the audience. I'm going to come on up. Somebody who will be able to help with the demonstration. You can tell us who you are, and you can stand over here.
All right, I'm Mary Liz Bender with the Planetary Society, and I'm very ready.
And I'll put you right over there behind. Great. Oh, do we need a match? Oh, we got it.
Okay, so as you saw in the video, the heat shield itself does have a white coating, and that white coating was specially designed for Parker Solar Probe. White is better at reflecting heat than black. It's a lot like being in a white car on a hot day as opposed to a black car on a hot day. It's just better. The heat shield itself is a sandwich panel. Sandwich panels are used commonly in situations where you need a lot of structure, but needs to be very lightweight. Aircraft are often made of sandwich panels, and actually Parker Solar Probe, the main bus, is an aluminum honeycomb sandwich panel. In this case, it's a superheated sandwich panel. So we have two outer face sheets. They're both carbon-carbon, which is a lot like the graphite epoxy that you would find in your golf clubs. It's just been superheated. In the inside, there's carbon foam, And the carbon foam is actually about 97% air, and it's just there to take that heat. It's a very efficient system, both structurally and thermally. As mentioned, the front surface is at about 2,500 degrees Fahrenheit at closest approach. The back surface, that back surface of the 4.5 inches, is about 600 degrees Fahrenheit, and the bus is sitting at about 85 degrees Fahrenheit. So it's an impressive thermal system altogether. So I'm starting to get this pretty hot. I can feel it. Yeah, the propane. So it's starting to get a little hot, a little red on the front surface. You want to take a touch of the back surface? See? I want you to touch the back surface, yes.
I'm going to actually touch it.
How does it feel?
Lukewarm, not even,
Normal room temperature. As you can see, it's glowing red hot on the front surface. You definitely don't want to touch the front surface of this. Okay, so I think I will turn this off. Just a little demonstration. Still cool? Still good?
Perfect.
Awesome. Thank you for demoing. So obviously this wasn't quite as hot as we get at the sun, but it's just a little demonstration of how well this functions. And Karen.
All right, you can stay up here with me because we're going to answer questions now. Maybe not with the blowtorch.
Yeah,
Drop your blowtorch. Great. We're bringing Alex Young back up, Nicky Fox. We're going to start with questions in the room. Already got some hands, so here we go.
Stephen Young with Astronomy Now and Spaceflight Now. As a science team, you must be pretty excited you're getting close to launch now. But I would imagine there are some pre-launch nerves as well. You've had some sensor problems and software issues that you're still working on. Could you give us an update on what is left to do to assure that everything's going to work as you intend when you launch?
Sure. I'm happy to say that Parker Solar Probe is inside the fairing. She is totally in her flight configuration. We have done all the work, all the checks. She finally looks exactly like I expected her to look from all those PowerPoint presentations I saw 10 years ago. All the blankets are off. The flight blankets are on. All the protective covers are off. We did have we were lucky enough to find out we had a issue with our temperature sensors. We had a great team that came in and put a totally redundant system in, so that is all good to go. All our flight software loads have been made, and she is buttoned up, looking beautiful, and totally ready to take her flight.
Yes, please.
Hello, Marcia Dunn, Associated Press. Science questions for either or both of you. On each orbit, generally speaking, how much time will Parker be in the corona? And, I read about the corona being millions of degrees hot. How is it that you're only experiencing 2,500 degrees?
That is a great question. I love that question. Yeah. So first of all, the prime science gathering, the instruments, the goal is to have them on us all the time, but the actual sort of prime science gathering for us is about 11 days. And we say it's from 0.25 AU, so a quarter of the distance from the sun to the Earth, around and then back out again. That's kind of our encounter period. And so, that's where we really consider the outer part of the corona and then coming right in and sweeping through. Yes, the plasma is at a few million degrees. And yet I said the temperature, and Betsy will kill me if I say only 2,500 degrees, because I'm not allowed to say that. But if you think of putting your oven on, and you set it at 400 degrees, and you can put your hand inside your oven and you won't get burned unless you actually touch a surface. And it really is the same. The corona is very tenuous plasma. It is not a hugely dense area. You need this entire sun to be blocked out by the moon to even see it. So it's not as dense. And so if you think about the amount of particles that actually are striking the heat shield and depositing that heat in, the whole thing gets heated up to 2,500 degrees Fahrenheit. But again, like I would just say, don't touch the oven surface, don't touch the 3 million degree plasma. But that's why it gets to 2,500 degrees.
I'm sorry, 11 days more or less.
Each orbit, yes.
Orbit.
Yes.
Okay, thanks.
More questions from the room? Yes, please, right there.
Thanks. Irene Klotz with Aviation Week. What's the nominal mission duration and the cost of the mission?
So the nominal mission duration is 7 years. And that is the 24 orbits, a little bit on the end to bring down our final data. And the official NASA cost for the mission is $1.5 billion. It includes the launch vehicle.
What happens at the end of the mission? What happens with the spacecraft?
So at the end of the mission, our last petal orbit, where we're in that final configuration, we are inside, pretty much inside the orbit of Venus at that point, so there's no more VGAs possible. But that last orbit is completely stable, and so we can stay in that orbit while we have the fuel to be able to maintain our attitude. Once we run out of fuel, the spacecraft will start to turn, and because they will no longer be able to keep orienting that heat shield. At that point, parts of the body that are not designed to see the full solar environment will then see it. The spacecraft will start to break apart. It will break apart into large pieces, and then it will get gradually smaller. And so I romantically like to think that she will become part of the corona and orbit the sun forever.
Thanks. And then I have one science question. The last time, Alex, I think we spoke was before the eclipse last year, and just was wondering, I know that was purely not for, I mean, science was made of it. It wasn't really intended for any science, but was there anything that came out of the studies that were done that sort of changed thinking or has any impacts at all in the thinking of this mission?
There's actually a lot of science. I mean, I could go on. So there's just the science of looking at the corona. Some of those results are still being processed because, in all honesty, there's so much data that they got during the eclipse from ground-based and aircraft that they're still processing a lot of that. So we're hoping to see some of those results probably actually in the next month or so. One of the first most fundamental things, actually, I think, was something Nicky brought up earlier, talking to the audience. The predictions from predictive science of what the corona would look like were amazing. The quality, the structure they saw, and what we actually observed were literally spot on. So that was the first science, really, that came from the eclipse. So that was fantastic. The rest of the science actually has a lot to do with the atmosphere. There's a lot of really interesting studies that were done of the atmosphere, the part that we live in here on Earth. When I say the atmosphere, Earth's atmosphere, but also the ionosphere. The science that was done to study the ionosphere was incredibly rich because it was across the U.S. and we had such broad coverage, radio coverage, in terms of the various types of radio arrays around the country in this particular part of the world. Gave us a detailed understanding of the ionosphere that we've never had. And we actually showed results from papers that were written 40, 50 years ago that were finally confirmed during that eclipse. So, so there's a lot of incredibly rich science, and it will continue to come out over the next couple of years.
We'll take one more question from the room now, some phone, and then we'll come back here.
Hi, Kent Kramer, Space Up Close, Rocket STEM. My question is specifically about touching the sun. I think it's the ESIS instrument.
Yes.
Can you describe how will that collect and analyze the particles?
Certainly. So there are, I mean, it is a complete suite that we're using to look at the various different aspects. The ESIS suite that you particularly picked on, they are looking at the very high energy particles. So the particles that are associated with shocks, with flares, with the coronal mass ejections that Alex showed all those beautiful movies. There is also the SWEEP suite, which is looking at the sort of the bulk solar wind. And so, you know, if you think of it as kind of the river flowing downstream, SWEEP has 3 different sensors that are looking at the stuff that's flowing all the time and sort of picking up all the little features that are in that continual flowing atmosphere away from the sun. And ESIS is kind of almost like looking at the motorboat that goes down the stream that is going much faster and much more energetically, but isn't always there. It's associated with these transients. The fields suite is looking at all the magnetic, electric fields and the plasma waves that kind of reside in, we think the magnetic field is the number one thing that's really causing these mysteries in the corona. And so highly important to be able to do that. The waves are floating around as the particles are changing. And then, of course, our white light imager that is taking those images of what the spacecraft is about to plow through. And so together, that is how we will answer all of these questions.
So there's like a porthole that collects the particles and...
There are apertures, yes, that the particles can enter through, and then they'll strike onto either charge capacitors, or there's different. We've got electrostatic analyzers, and yes, and the solar probe cup. Obviously, it's striking the grids and looking for the voltage signals.
Thank you.
Great. We're going to go to the phones now with Stephen Clark with Spaceflight Now. You can ask your question.
Hi. Thanks for taking my questions, if I may. First, to follow up on one of my colleagues' questions about the temperature sensors on the spacecraft. I think Dr. Fox mentioned some redundant system was installed. Can you expand on that? Did you install new sensors in the clean room, and what was the actual original issue or concern with that? And secondly, I'm wondering just some information on the timeline of the mission. I know you're first later this year. Can you talk about what kind of science you're going to get early on, and a few months after launch, and then how the science may improve as you dip deeper into the corona over the next 7 years? Thank you.
Yes, sure. So yes, the temperature sensors, we did find an issue. We had a number of them that had failed during testing, and we were able to put a new system that basically they're located in the same sort of real estate next to the original ones, and as anything fails, it rolls over onto the new system. And so we've done a full testing of the second system, and we're very confident. And we've done many good tests to show that both of those systems are now working well. And any issue we roll over to the new system. So that was a good catch, good find, and fantastic effort by the team to rectify that and keep us on our march towards launch. You asked about the science. So we will actually, in our very first flyby of the corona, we get to just it's a little more than 15 million miles away from the sun's surface. So we're still 3 times closer than anything has been before. And so we're already in a region of very, very interesting coronal area. In fact, one of the key things about our early orbits is we're actually just at this sort of sweet spot where the plasma that we're flying in through a flux tube, and we stay in the same flux tube. And then as we're rotating around the sun is rotating at the same time, the same speed. So, if you think of it in that frame, the spacecraft is staying over the same area of the sun for many, many days, allowing us to do some really incredible science on our very first flyby.
And I wanted to add something, just because the eclipse was mentioned. We actually have an incredible opportunity, so that while the observation times are not a one-to-one correspondence, Parker will be looking at the corona and flying through the corona near the time of 3 total solar eclipses, including the 2024 total solar eclipse in the United States. So we will be measuring the corona, studying the corona up close and personal, and we'll be looking at it with incredible detail here on the ground during total solar eclipses. And that is a first.
Yeah, that is fantastic. Yeah.
We have another question from the phone. This is Jim Siegel with Spaceflight Insider.
I have a question relative to one of you mentioned earlier about one of the hazards of solar winds and solar climate is how it affects the power grids here on Earth. And so I'm interested in how frequently that occurs, if at all. Have there been any, for example, big examples of that in the recent past? And I'm also wondering, given maybe our more reliance increasingly on the solar grid, do we expect that without this information from this mission, our solar grids are going to be more vulnerable in the future because of our greater reliance on grids, power grids? So that's it. Thank you.
All right, I'll jump in first and then let Alex jump into. So yes, we are, as a society, we become more and more reliant on technology. And so what in 1859, when we had the Carrington event and the telegraph system went down for a few days, that was terrible at the time, but you try telling your kids now they're going to lose their internet for 4 days and national panic will ensue. And so we have a very, very, very different way of the way we live now. And so yes, we are totally reliant on power grids. And yes, a big aurora, beautiful aurora, is like having a big current flowing through the sky, and currents have to find somewhere to close. If the ground underneath you is non-conducting, they will look for something long and straight and conducting that they can flow through, like a power grid. In 1989, we had the famous Hydro-Quebec power failure, it was a catastrophic failure of the entire grid, and 6 million people were left without power for many days. And so, yes, we do have these things. We are right now in a period of somewhat quiet solar conditions. Not that we haven't had recent events, but we are in somewhat more of a quiet. The big thing for Parker Solar Probe is, if you think of the sun and the earth as a system, we understand all of the pieces, but we don't have the physics that drives the solar wind. And so by doing this mission, we're going to go make those measurements, understand what we should be putting into those predictive models. And that is how Parker Solar Probe will help protect society from the vagaries of the sun.
Yeah, so Nicky covered the main point, but it really gets down to the fundamental physics. A great deal of what we can do now in terms of space weather prediction is statistical. We can't do much better than, saying there's an 80% chance of something. That's just based on past conditions, just like when we do prediction of the rain. All we can say is the conditions were like this in the past, therefore 8 out of 10 times it rained, therefore is 80% chance of it rain. That's not really getting to the fundamental physics of why. And so now that we're going there, we're going to be measuring the fundamental processes that are happening at the source. This is going to provide unique input into models that will lead us to the point of actually truly being able to maybe make real predictions, not just on a statistical basis, but on a physics basis, and that's the key.
Thank you. We're going to take 2 social media questions, and then we will come back to the room. I know there were some more questions here. Please.
All right. Jamie on Twitter would like to know, was the Delta IV Heavy rocket picked to launch the probe for any special reason?
Yes, the Delta IV Heavy was picked because we need to have an incredible lift, a real sort of big Delta V, a real big kick off the planet. And so not only do we need all of the awesome power of the Delta IV Heavy, but I mentioned we also have the third stage, which of course fires when we're already outside the atmosphere and gives us more than half of our Delta V, actually. But yes, the Delta IV Heavy took a lot of strain off that third stage by providing it that extra power. And so we are using every single drop of the Delta IV Heavy. As Betsy mentioned, we have to be as light as possible just so we can lose the momentum of the Earth and be able to go into the sun.
Thank you.
Christopher from Facebook, will there be any science gathered during Venus flybys?
The science during Venus flybys, for most of our flybys, that's actually during our prime downlink of our science data from the corona. As Patrick mentioned in his video, a lot of the times the sun is between us and the satellite, and so it's very hard for us to be able to see and close that link. And so whenever the spacecraft comes close to the Earth, we pull down all that data. Most of those Venus flybys are during that period, and our instruments are switched off so that we can put all the power to getting our coronal data down. There is I think it's the 6th VGA where we will have the instruments on. We're not downlinking data, and so we'll be interested to see what measurements we can make as we whip past Venus on that one.
Great. Let me bring it back to the room. Some questions here. Yes, sir.
Hi, Emery Kelly with Florida Today. As I understand it, it's highly unlikely, but as I understand it, the launch window for this mission closes August 19th, August 20th. Worst case scenario, what happens if that happens? And second question, obviously there are a lot of moving parts to this mission. in terms of anomalies, what are you possibly expecting? Thanks.
Sure, I'll take the launch window one. August 19th, you are correct, is the date. There's always the chance we can push for a couple extra days, but that is our window. And of course, the whole point is we have to get to Venus at the right time, so would have to adjust for a different launch time for that planetary necessity.
As far as anomalies, in the beginning, it's pretty standard spacecraft anomalies. If something doesn't work exactly as you think it does, it's really hard to predict. I mean, we've operated a lot of spacecraft, we've launched a lot of spacecraft. We know the type of things that can happen, and we're ready to watch for it. It's really no different to any other mission for making sure that you've got all your fault management system and everything is all buttoned up and ready to go.
All right, another question here.
Stephen Young with Astronomy Now and Spaceflight Now. For Nicky, the wide angle camera that you have on board, what will that see, and what sort of wavelengths are you looking in? And will we see those things, and will they be blockbuster images that we'll all be very impressed by?
Well, I'm going to love them. So it's a white light imager. And so it will look very similar to the corona that you saw during an eclipse, only yet even more tenuous as it moves away. And so there are some very nice images from the stereo spacecraft. Craig DeForest, a researcher at Southwest Research, has just published a really nice paper looking at some of the structures that he got from these stereo images. And so it's like, it looks like maybe dust flowing fast, but to us we can see structures in that sort of, you can see like little particles. And so it's important for us because, these instruments, this is the first time we've gone into this region of the unknown. We are traveling at roughly half the solar wind speed. I mean, I mentioned 430,000 miles an hour, and the solar wind's traveling at roughly 1 million miles an hour. So sometimes we're traveling in the same direction, and so all the features will get kind of smeared out. And then other times we're ramming into it, and everything is going to get really sort of compressed. And so having that imager to be able to show us, oh yes, that's it. Look, it's a flux rope, and it's a flux rope, yes. And so it's really, because a flux rope's going to look very different when it's this big to when it's this big, depending which way you're traveling. And so being able to see what kind of structures, what transients, what is flowing towards us is really important. It is not going to look like an SEO image, nor indeed my dress. It's not going to look like that. We are actually we are blocking. We use baffling to make sure it doesn't see the sun. So it's more like a traditional coronagraph, but tuned to see that more tenuous atmosphere that the spacecraft will see on for most of its orbit. But I would say spectacular coronal images, but I'm a little biased. So.
Great, we're going to go to a phone question now. Space.com is on the line. You can ask your question.
Hi, thanks so much for taking the time. I wanted to talk a little more about the autonomous decision-making abilities of the spacecraft. Could you explain a little more what that process will entail in addition to regulating the thermal input of the satellite, but what other factors that will play into?
Yeah, I mean, there's a really simple example, which is there are 7 sun sensors located around various parts of the spacecraft, and none of those sun sensors should ever see the sun. The moment one of them does, the spacecraft knows, hey, this one, I've started to tilt in this particular way. I need to fire a thruster. I need to, make the momentum wheel go faster. And so all those things are sort of programmed, pre-programmed, and unbelievably tested, as you can imagine, to make sure that so that is sort of one nice example of the autonomy. There's also things like making sure we know how much power is coming off the solar panels. If it increases over a certain level, then tuck those solar panels in. The video was a nice demonstration, and Patrick also talked about the fact that the solar cells are sort of articulated like on shoulder joints, and so we can tuck them in until it's just like your fingertips are sticking out. So if we suddenly see too much power, the spacecraft can adjust those solar panels. So there are a couple of examples.
We have another question on the phone from NASA Spaceflight. Go ahead.
Yes, thanks for doing this. A follow-up with the autonomy question and then a follow-up after that. So for the autonomy portion, am I correct that there are still elements that if something goes wrong during these coronal deep dives, that the probe will still enter safe mode to protect itself at all costs until it can swing around and a human would be in the loop? And then a follow-up to that is, can you talk about some of the space-based applications for the technology of the sun shield and the radiation shielding for other satellites and some of the more practical applications that the technology on Parker Solar is demonstrating?
Okay, so I'll take the first part and say that, yes, we also, in addition to this sort of super duper autonomy, we also have the more standard, if something happens, you safe and protect until, somebody can get in the loop and look at that subsystem. So for the instruments, for example, if they saw a problem, they would take down a high voltage, or they would, do something to protect themselves. So they will survive their journey through the corona, and then we could do analysis on it outside, which is like pretty much any mission that we fly. The addition here is all this ability to keep the attitude system absolutely perfect. And then Betsy, I'll let you take your baby heat shield and talk about that.
So the heat shield technology itself, while different than any heat shield that's been built before, is built on some of the materials and technologies that have been used before. The lead engine of the space shuttle, or the lead edges of the space shuttle, actually are a heritage of then some of the materials you see here. And some of the development that we did has a good understanding of how we might do heat shields in the future in lighter weight ways, more efficient ways. Additionally, the autonomy system, which, like Nicky mentioned, is most autonomous spacecraft that's ever been built, learned how to do that, how to do fault management, and that will flow through to future missions and how we actually run spacecraft in the future and kind of change our capabilities.
Thank you. We have a couple more questions in the room, but we're slowly running out of time. I want to give the AP a chance, and we'll do one social media. And if we don't have a chance to answer everyone in the room, there will be some availability afterwards to talk here.
An AP with two quick questions. It's sort of an odd-shaped shield. How many sides is it? Is it really an octagon or something else? And then if I'm looking at last summer's total eclipse, and I'm looking at the little wisps of the corona, how deep into that picture will you be?
All right, so let me take that one because that's really easy. Do me a favor. When you leave this building, go into the bullpen, and in there you will see a model that was made, as Alex noted, the predictive science who really predicted what the coronal field would look like. In there you can see a scale model, sun in the middle, all of the field lines draped out, and Parker Solar Probe sitting right there. So it is 4% of the distance. I have a great graphic I can show you on my computer afterwards. But the long streamers, the very long ones, Parker Solar Probe is right on those streamers. Not the super close, sort of the more halo, but the long helmet streamers, Parker Solar Probe is well on those. But do take a look at the model on your way out.
And I'll let you finish, but I'll just add, and when you are observing, hopefully the eclipse, really, really good conditions, you will be looking at the edge of it. So it's something you can physically see from the ground.
Yes.
The edge of your field of view on a good observation time, you will see where Parker is.
Yeah.
And the shape. So the shape is very odd. We were talking about the mass being a critical thing on this mission, so it is perfectly designed to cover what it needs to cover. It's actually not even, it's hard to see with your own eye, but it's actually not even symmetric, and it's not an octagon. It's got two rounded edges with some tangents, and then there are basically 6 flat surfaces, 2 very long flat surfaces, which are giving our knife edges, as we call them, for the solar rays. Nicky was talking about having a very precise, and Patrick did as well. We use those to very precisely control how much energy is making it into the solar rays. So that's why you have those long flat edges. And then the 4 kind of shorter flat edges are actually for the solar limb sensors that we were talking about and how we actually can go understand when something is being illuminated. So every surface on that shield is designed to either protect or perfectly enable something below it.
Great. Social media next.
Yes. Dana from Facebook asks, was the project timed to coincide with any specific part of the solar cycle?
It was not specifically targeted, but golly, we're happy where we are. So I would say it's serendipity that we are launching right before solar minimum. Solar cycle 11 years, we're a 7-year mission, which means we will go from solar minimum and crest solar maximum, and then, hopefully be able to go even a couple of years beyond that within an extended mission. And so it's a happy accident. We're delighted. It was not planned that. I wish I could say yes, we planned it that well, but it's really, really fantastic for us exactly where we are.
To cover more than half a solar cycle is incredibly powerful for the science.
Yes, and to do the minimum to the maximum, not halfway up across maximum and down, is really fantastic for us. Yes.
All right. We'll do one more question in the room, and as I say, we will have people available to talk afterwards. There are a whole bunch I'm going to give you since you haven't asked one yet.
Thanks so much. Joey Roulette here with Reuters News. Would you say this is perhaps the most ambitious project under the Living with the Star program? And I don't know if this was mentioned before, but how soon will we get the first pings of data back from the probe?
Honestly, I would say every mission that NASA does is ambitious. It's what we do. We push the boundaries, we push technology, we do everything else. Certainly to send number one, to send a probe where you haven't been before is ambitious. To send it into such brutal conditions is highly ambitious. SDO and Van Allen probes are doing fantastic things, and I would hate to say that they were not ambitious. SDO had an incredible challenge of bringing down terabytes of data every day and had to figure out how to do that. The radiation belt storm probes, sorry, I'm old school, the Van Allen probes, it rolls off the tongue too easily for me. The Van Allen probes live and work in regions that most spacecraft try and avoid. And so I think all of them are doing incredible cutting edge science. They've all had their own challenges. The solar probe is very much at home in a group of challenging missions. And your first peeps of data, we should get our first data down early-ish December. Yeah.
Great. That is all the time we have for your questions right now. We are going to remind everybody you can watch the launch. It is on the morning of August 6th. The window opens at 4:08 a.m., nice and early in the morning. You can watch that at nasa.gov/live. You can stay in the conversation using @NASASun, and we look forward to continuing to answer your questions as needed. We are going to end our TV broadcast with a message from our Associate Administrator in the Science Mission Directorate. This is Thomas Serbukin, who has recorded a message for us from NASA headquarters. You can roll that.
Hey, I'm Thomas Serbukin, the head of NASA's Science Mission Directorate and a solar physicist. The Parker Solar Probe mission is heading to a region of space never explored before. This is truly a mission for all humankind and will forever change how we view the sun. Parker Solar Probe is the newest addition to NASA's heliophysics fleet. These missions study the vast interconnected stretches from the sun to the space surrounding Earth and other planets to the farthest limit of the solar system, where the sun's constantly flowing streams interact with the galactic environment. Parker's data will improve forecasts of major space weather events that impact life on Earth and satellites and astronauts. It will help provide situational awareness needed for future missions to the Moon, Mars, and beyond. While we have many missions dedicated to studying the sun from afar, we have never, ever had a mission to get this up close and personal. Just think for a moment, when you look up and see the stars, they are so far away that with current technology, it will take millions of years to get close enough to study even the nearest one. However, we have a star we can travel to and begin studying in mere months. That's our sun. You're probably thinking, why do we need to touch the sun? Well, by studying our star, we can learn more about all the other stars throughout the galaxy, the universe, and even life's beginnings. This mission has many firsts, including the namesake, Eugene Parker. In fact, this is the first time NASA has named a spacecraft for a living individual. It's a testament to the importance of his work founding the field of science that inspired many important science endeavors, including my own research. Parker Solar Probe will face intense heat and radiation unlike any spacecraft in history. But don't worry, the instruments will operate at room temperature, most of them at least. This is possible with cutting-edge thermal engineering advances that will protect the mission throughout its trailblazing journey. Finally, this year marks NASA's 60th anniversary of research and exploration and has fundamentally transformed our understanding of Earth and the universe we live in. Parker Solar Probe will now join that unprecedented NASA history by helping us answer questions about solar physics that we've puzzled over for more than 6 decades. The investments in this mission will return a better quality of life and create knowledge and drive inspiration that benefits all of humanity. Thank you for joining us today to learn about NASA's Parker Solar Probe, a mission to touch the sun, a mission to touch us all. Go Parker Solar Probe.
Welcome and thanks for joining us. We are coming to you live from NASA's Kennedy Space Center in Florida, where for the next hour, you will hear about humanity's first mission to touch the sun. You're going to hear from presenters that will tell you the how, the why, and much, much more. All systems are go for a scheduled launch of the wee hours of Saturday morning, August the 11th. And we are going to bring to you some incredible things leading up to that launch. Joining me today, back on stage after the eclipse of last year, Karen Fox. Karen Fox, it's sun time again.
It is sun time. We are going to the sun. We will be taking your questions. Social media can take questions if you're using the hashtag AskNASA. And we are going to be talking about this incredible trip. We're going to the sun. It's going to get within under 4 million miles at the closest approach to the sun.
Right. And, you know, Karen Fox and Dwayne Brown joined together again, but let's bring up some of these cool mission team members, and we're going to learn about humanity's first mission to touch the sun, right?
All right, so we're going to be getting to within a distance to the sun that is under 4%. So if Dwayne stands over there and he's the sun for a moment, and I'm over here, and I'm Earth, 4 million miles does not sound so close, right? But actually, it is within under 5% of the distance to Parker Solar Probe will be coming really up close and personal to the sun. We're going to be going right through the corona. That is the solar atmosphere you can see during an eclipse. And it's going to be facing brutal heat, brutal radiation conditions, giving us our first ever view of the star that we live with.
Let's get started and hear about the Parker Solar Probe mission. So, first up, the head of NASA's Science Directorate and has an incredible portfolio of over 100 missions. You guys have seen him a lot on television, and he's pretty much a rock star across the world. Please welcome to the stage. He's so cool, he goes by one letter, Dr. Thomas Zabukan, but we call him Dr. Z. Welcome, Dr. Z, to the stage. Dr. Z, 100 missions, but when you talk about this one, you have a big smile, but you made history about that mission. Could you tell the audience about that history-making decision?
History has everything to do with the name on that mission. I'm just so glad you're here, Gene. That means a lot to me personally, but it means a lot to the entire community. Good to see you. This is the first time there's ever a launch of a mission and the name on the mission is represented right in the room. We've never done this, we've done it here. And why did we come up with that idea? Frankly, there's no other name that belongs on this mission. It's absolutely clear that it's Gene Parker's name. And the simple reason for that is a paper that he wrote in 1958, a paper that I taught in school many times to hundreds, if not thousands of people. But it's a paper that made history because, if you want, it filled the space. The paper was a prediction about the solar atmosphere that expanded and filled supersonically space everywhere, the solar wind. And that solar wind between the planets, of course, was described by a simple set of equations that you saw on TV just recently. Those equations tell us a big story. They tell about, of course, the particles that are there, the field that is being pulled out of the sun together with that plasma, but also talk to us about the threats that come from this plasma, from these particles that we think about as space weather. As a technological society, what comes towards the Earth matters. And that's what Parker means to us. I want to tell you also that in addition to this particular paper that Gene Parker wrote in 1958, of course, he basically was a pioneer in plasma astrophysics. He talked about the fact that magnetic fields are important when you look at the universe. And so I did a tally with my team and basically said, how many missions do we have in our mission portfolio that directly are involved in looking at things and measuring scientific phenomena that are predicted by Gene's papers? And the answer is 35. 35 missions are covering this both here in our environment, heliophysics missions, but also in astrophysics and missions in planetary sciences that do the very things that Gene Parker talked to us first.
Thank you so much. Let's have another round of applause for Dr. Z. Thank you. Next up, we have a woman with a fantastic last name. This is Nicky Fox, no relation to me, Karen Fox. Nicky Fox is the project scientist for Parker Solar Probe at the Johns Hopkins Applied Physics Laboratory. Take it away. Tell us what this mission's going to do.
Thank you. So yes, as Thomas said, this is a mission that has been in the making for 60 years. We've had to wait so long for our technology to catch up with our dreams. And why are we doing such a daring mission? We know a lot about the sun. It's just over there. We see it every day. But the sun is full of mysteries. One of those mysteries is that the corona, that lovely atmosphere that we all saw during the total solar eclipse last year, that is about 300 times hotter than the surface surface of the sun, and that just doesn't make sense. And so we need to go up there and figure out why that's happening. The other thing, of course, is we need to really understand why, as Gene predicted, why this atmosphere is continually expanding and continually accelerating away from the star. The only way we can do that is to finally go up and touch the sun. We've looked at it, we've studied it from missions that are close in, even as close as the planet Mercury, but we have to go there. And so how are we going to do it? So we'll launch from Kennedy on Saturday morning on our beautiful Delta IV Heavy. And the first thing we will do when we get on orbit is encounter the planet Venus. We use Venus to give us a gravity assist, if I could have that Venus thing. We do a little gravity assist. It's a bit like a handbrake turn. We're not like those other missions. We don't take energy from the planet. We give it generously. And we actually slow down just a little bit. And that allows us to shrink our orbit and go closer to the sun than anything has been before. Even in our very first flyby, we will be well inside the solar corona and taking data in that key region. If you look at my dress, Parker Solar Probe is about at the right scale. So we will go hotter than anything has been before. We're in that 3 million degree plasma region in the corona. We're moving faster. We're moving at about 430,000 miles an hour, or about 118 miles a second. And we're going closer, as Karen already said, to 3.83 million miles above the sun's surface. So we'll use 7 Venus gravity assists. We'll gradually walk closer. We'll take sort of 7 giant steps closer to the sun until we're in that final region. Of course, we wouldn't go there empty-handed. We carry with us an amazing payload of instruments. And those instruments are designed to make those critical measurements that we have waited so long for. We have particle instruments that will measure the continually flowing atmosphere that Gene predicted in his 1958 paper. We'll also have particle detectors that are looking at those high energy particles associated with shocks and flares and coronal mass ejections and transients that we see in the solar wind. We know the magnetic field is the real key. We know that this is why we're making this daring mission. We're going to go into the transition from where the magnetic field is dominant to where that coronal material dominates the magnetic field. We need to measure the magnetic fields, obviously. Where you see changing magnetic fields, you see changing electric fields. We got one of those too. We'll also be listening for plasma waves that we know flow around when particles move. And last but not least, we have a white light imager that is taking images of the atmosphere right in front of the sun. It's not taking pictures of the sun. We actually are blocking out the sun's light, and it's taking images of what the spacecraft is about to plow through. So really taking the first close-up images of the sun's corona. And so we are ready. We have the perfect payload. We know the questions that we want to answer. And so we will go with Parker Solar Probe. We'll unlock the mysteries of the sun and the sun's corona, and we will touch the sun. Thank you.
Nice round of applause for Nicky Fox. These folks really dressed for the occasion, and you'll see why. You saw Nicky's dress, and check this, this gentleman coming up. So if you're just joining us, we're coming here live from NASA's Kennedy Space Center in Florida. My name is Dwayne Brown with the Office of Communications with my colleague Karen Fox. So you heard Nicky tell you why we're going. Now you're going to hear the how. Please welcome to the stage someone who is very, very familiar with the spacecraft, the project manager from the Johns Hopkins Applied Physics Laboratory. Give it up for Andy Dreisman.
Thank you, Dwayne. Thank you.
Now, Andy, before I leave, you got the tie. This tie is slanted, right? Okay.
Well, this is, my wife got this for me for Father's Day, and this is, I think, her attempt at making me fashionable. You could decide for yourselves whether she succeeded or not. And I'll mark, in the back, 2018. So we're here, 2018. So thank you, Dwayne. Thank you all. So I'm going to spend a couple minutes telling you about all the technology that went into developing this spacecraft. So 4 million miles, the sun is hot. Outside, you go outside of Florida today, the sun is hot. 4 million miles, the sun is very hot. So we need to bring an umbrella with us. So just like you might wish you had an umbrella out there in the hot, sunny day, flick open your umbrella. We bring an umbrella, only the umbrella is a heat shield. It's a carbon-carbon heat shield. It took about 18 months to fabricate this heat shield and over a decade to develop. The carbon, it's only 4.5 inches thick. It's got carbon phase sheets on either side, and it only weighs 160 pounds. If you had tried doing this mission in the 50s or 60s or 70s, you'd be building big metal heat shields. So carbon is the magic material. One of the other enabling technologies is the solar arrays and the solar array cooling system. Like any other satellite, we need to generate electricity to run the systems on board. We have solar arrays, they come out and they peek their little edges out behind the heat shield very gingerly, and they have to deal with the full solar environment. A normal solar array would burn up quickly. So we have a solar array that actually has active cooling in it. There are 2 pumps in the spacecraft that pump water through the cooling system, through the solar array, and they pump it out through radiators. So much like your car stays cool on a hot day like today, that's the way we keep the solar arrays cool. The final technology, and this is what we would call a distributed system, is the fault management or autonomy. Because of the orbit around the sun, there are long periods of time where we can't talk to the spacecraft, and the spacecraft can't talk to us. We're blocked out by the sun's radio noise. So this spacecraft has to be fully autonomous. Plus, we've got at times 16 minutes of round-trip light delay. So even when we can talk to the spacecraft, it takes a while to do it. And so the system is designed to protect itself. On board the spacecraft, we have sensors called solar limb sensors. These were a new development item. And if the solar array were to lose attitude, where that umbrella started rotating away from the sun and parts of the solar spacecraft started coming out from behind the umbra, the solar limb sensors would pick that up. And they are the first thing to pick it up. They're robust to the solar environment. And what they do is they protect all the sensitive parts of the spacecraft from coming out into the full sun. The last thing, and probably the most important thing that I'd like to talk about that was enabling, was the team. The team that developed this has been working specifically on this for more than a decade, but from the science community and in some of the engineering community, it's really been 60 years. You could trace back papers and read engineering reports from the 60s and 70s about this mission, about different concepts and different ways of being able to get to this environment. The team that developed this is a team of thousands from around the world. I did a little math about 3 weeks ago, and I took the budget and just divided by the number of hours, and it was 3 million hours, almost 4 million hours of labor, 4 million staff labor hours from the start of phase C to where we are today. And that team is really what enabled Parker Solar Probe to be what it is today. So thank you, Dwayne.
Another round of applause for Andy Dreisman, project manager. Okay, so Andy, come on back and the other team. Now we're going to transition into the Q&A with this incredible team, and then we're going to go to our second part of the show. What we're going to do is we're going to start here in the audience. Then we're going to go to social media, and then we're going to go to the phone bridge. So, and please wait for the mic, give your name and affiliation, and if you can address it to a specific person, that'll be great. We're going to take a few minutes for Q&A, and the gentleman at the hat here. Name and affiliation, please.
I am Jim Siegel. Yeah. And I'm with Spaceflight Insider. I have a question about the spacecraft itself. I believe it's going to make 24 or so circuits through the corona. What happens to the spacecraft after that?
So that's correct. It makes 24 orbits around the sun. 7 of them interact Venus. And on orbit 24, what I'm hoping is we're going to continue to go. I mean, as long as we have propellant on board, we're going to continue to take science data. Eventually, the spacecraft will run out of propellant. At that point, at some point in the future, it'll lose attitude control, and those sensitive bits of the spacecraft, which we work so hard to protect, will eventually transition to the sun. So the way I like to think about it is that in hopefully a long, long period of time, 10, 20 years, there's going to be a carbon disk floating around the sun in its orbit, and that carbon disk will be around till the end of the solar system.
Marcia Dunn, Associated Press. You couldn't have asked for a better opening act last year with the Eclipse, as was mentioned. Do you really think that sparked a lot of more interest in this mission and brought a lot more attention to what you're about to accomplish?
Yes, I do. I mean, I think that it made everybody look to the sky It made everybody realize that the sun is not just a single point of light, but it has profound effects on us here at Earth. Thomas talked about some of the catastrophic events with the space weather that we see, and it really did bring up an awareness. I mean, it's a beautiful sight. My goodness, we saw the corona. I got very excited, but we saw the corona, and you don't see that every day. Well, Parker Solar Probe is going to be in there, and I think just realizing that we were sending a piece of technology that is going to go into that region that was visible during that amazing eclipse. To me, it's still mind-blowing, and I've worked on the mission for 8 years, and even I still go, really? We're doing that? I think it did an awful lot to really bring up the awareness, but also for the entire heliophysics and the amazing fleet that NASA has. And with that, I'll throw it to Thomas.
To me, my experience during the eclipse was just that. So first of all, I actually didn't realize how emotional I'm going to get when I've been studying the solar corona for 20 years, and I saw it for the first time with my eyes, right? It's like, that's an amazing moment. But I remember, actually there's video footage that says that within seconds of that, it's like, this is where Parker's going to go, right? You immediately see it's like, you see it there. It's totally in the dark there. That's how close it's going to be. And so for me, that, I think, made a huge difference. I do believe, actually, the name made a huge difference, too, for many people. Kind of stories, personal stories attached to this story of perseverance, of innovation, a story of being right, ultimately, in the face of adversity. I think those stories, they matter. And they're stories that are out there in the community, and we all resonate with. And I think the final part is just really, once you come up with the recognition that it really is the equivalent of touching the sun, kind of flying through its atmosphere. Kind of, that's the spark, right? Kind of, it's like it pulls you in that emotional state that you can't forget the mission about. So what we're recognizing at NASA is this is one of the missions that has a tremendous following, tremendous excitement, and kind of over and above many of the other missions that we have, just because of this trifecta, I would argue, of values.
And Marsha, stay tuned, because in discussions, they're doing something pretty special on the anniversary, which is in a few weeks, for the solar eclipse on August 21. So you guys stay tuned for that. What we're going to do is take one more question, then we're going to go to social media, then we're going to go to the phone bridge. Name and affiliation, please.
Ranvir Arisene with the Astronomy Outreach of Kosovo and the Talking Space. So since these sensors will be kind of outside the edge of the main heat shield, what's stopping them from melting, and what are they made of exactly?
So most of the instruments, as Andy noted, are on the main body of the spacecraft, and they are at a very balmy 30 degrees centigrade, 85 degrees Fahrenheit, compared to the 2,500 degrees Fahrenheit that our heat shield is seeing. We do have the 4 fields whips that stick out. They are made of niobium, so they are very thin tubes. They get hot, but they're not so difficult. The Solar Probe Cup is the bravest little instrument on the spacecraft. It bravely peeps around the heat shield, and it is a fairly big instrument. And so there was an enormous amount of testing that went into that. It is made from some pretty exotic materials. It has molybdenum, it has molybdenum, it has niobium, and it also has a lot of tungsten. And so it had to go through a very, very, very rigorous test program. In fact, they even designed their own test facility at the Smithsonian Astrophysics Observatory at Harvard, where they could really create the atmosphere that it was going to have to see every day to make sure that it wouldn't do anything bad.
Great. Let's take some questions from the social media folks in the room. Do we have a question here? Yes, sir. Please wait for the microphone. Oh, sorry.
Thank you. Chuck Fields, Online Coffee Break. I had a question. I understand the carbon-carbon is going to protect the spacecraft, but what's the duration of the spacecraft when it goes through the corona? I understand it might vary on each orbit, but how long will it actually be in the temperature of the corona?
So the spacecraft's in elliptical orbit. Think of it, its furthest distance from the sun is around Venus, and then every time it flies by Venus, the perihelion, or closest approach, gets lower and lower. From our perspective, the science taking is from a quarter AU on the inbound to a quarter AU on the outbound, so a quarter astronomical unit. I believe that the spacecraft's always in the atmosphere of the sun, as is the Earth.
I would argue that, yes, strongly. Always. We live in the atmosphere of the sun.
We do live in the atmosphere of the sun. Thank you very much. So it's about 12 days is the way we think about it.
Okay, we're going to go to the phone next, and then we'll come back for social media. I know we have a lot of questions. We may not get to them, but we have some other opportunities to answer your questions. So we're going to go to the phone bridge, and I believe we have Denise Chow from NBC News. Denise?
Hi, thanks for taking my question. With the Parker Solar Probe sort of set to become the fastest ever human-made object, I'm wondering if you can comment on that milestone and also talk a little bit about the challenges of designing something that will be traveling that fast in space.
It will be the fastest human-made object at 430,000 miles per hour. That's on its last orbit. Well, it's third to last orbit at the closest approach, and at perihelion. Designing something to go fast in space is pretty much the same as you would design it to go slow in space. Space has nothing to really impede its progress, the spacecraft's progress. So from a speed perspective, there isn't much of a concern. The spacecraft doesn't know it's going fast. What is maybe more interesting and a little esoteric is that around the sun there's a hypervelocity dust environment. So that's really what this, the speed gets you. So the spacecraft intercepts dust particles, and the spacecraft has shielding on board. It's built into the blankets. It's built around the cooling system. And this Kevlar shielding protects the spacecraft from this, what we call hypervelocity dust environment. So that's probably the biggest impact, no pun intended, of going fast.
We have one more question now from the people who have been using hashtag AskNASA to ask a question. So let's go to that question, and then we will be taking questions at the end again.
Back in March, members of the public were invited to send their name to the sun aboard the Parker Solar Probe spacecraft. Twitter user David, who goes by @KnowStuff on Twitter, asked, what will happen to all of our names aboard the craft?
So your names will continue to orbit with the spacecraft, and even after we have no fuel, as Andy said, he thinks about the carbon disk circulating, going around the sun. I think of the spacecraft will break up into large pieces and then smaller and smaller until it becomes part of the dust cloud. So your name is going to orbit the sun forever.
Fantastic.
Okay, so let's take one more question, and then one more. Then we're going to wrap up and bring you the second part of the show here. Right here with the mic. Where's the mic? Oh, you have the mic.
Hi, Ken Kramer, Rocket STEM and Space Up Close. Thanks for doing this. You talked about took 60 years for the technology to catch up, and you mentioned specifically the heat shield. What else on the spacecraft, maybe the science instruments, took 60 years of development?
I mean, certainly finding the right materials. It isn't just a case of surviving those incredible heat when we're close to the sun. As we've all mentioned, we come out around Venus and it's cold there, which means that these materials have to withstand heating and then cooling, very, very, very extreme changes in temperature, 24 and then apparently another 10 years beyond that, according to Andy. So, they have to be incredibly durable. So certainly the materials, and then I often liken, 60 years ago, if you wanted to make a phone call, you had a rotary dial phone that was on your kitchen wall. Now we all use smartphones, and we use them, I bet you, for everything other than making a phone call. If I have to make a phone call, I've broken down any other way of communicating with somebody, and now I've actually got to call them. Because of the way our technology has changed, the way we live has changed. And if you think about the technology you hold in your hand, in your iPhone, and you compare that to what that would have taken in 1958, you're talking city blocks worth of buildings of that type of thing to be able to do the autonomy that Andy was talking about. So there are, lightweighting, miniaturization, materials, everything that goes into making the spacecraft small, compact, and light enough so that our wonderful launch folks can give us the kick we need to go into orbit.
Do you mind if I add one point about the instruments? I really believe that, I think just in the same realm as Nicky talks about the spacecraft, the instruments have also benefited from multiple generations of instruments that have flown on spacecraft that are, say, spacecraft like Stereo, spacecraft like Wind, or the Advanced Composition Explorer, or others, in which some of these instruments were for the first time really perfected and then integrated and made smaller. the instruments are in every way as advanced as the mission that the spacecraft is around it, I would argue. Kind of a really top-notch instruments that with the mass that is available, which of course is limited because we want to use every single pound for fuel, right? Because we want to go in there with that, within those limitations. Those are instruments that were not possible to build even 40, 30 years ago. We had to do the other ones first.
Okay, that's going to do it. Please give a nice round of applause again to Dr. Z, Nicky Fox, and Andy Dreisman. Thank you all.
All right, we are going to get started next talking about the launch itself.
That's right. And if you're just joining us, again, we're coming to you live from NASA's Kennedy Space Center, where we're just a few days away from an early morning launch of humanity's first mission to touch the sun. My name is Dwayne Brown with the Office of Communications, my colleague Karen Fox. So we've heard about the science and everything. Now, the folks that are going to make some noise and fire and all this good stuff. The person who I've had the honor of working with many years, the launch director for this incredible mission. His name is synonymous with great launch missions. Please welcome to the stage the launch director for the Parker Solar Probe mission, Omar Baez.
Thank you. Thank you for all attending. It's a pleasure to be here. I'm super excited. This is the first time that NASA is launching a Delta IV Heavy with a third stage and flying a science instrument on board it. We've flown other Delta IV Heavies, but not with science. And this is really cool to be able to get science that Gene here envisioned 60 years ago and finally getting it to fly. I work for the Launch Services Program here at NASA Kennedy Space Center. I am fortunate to be the launch director. I've been the launch director on numerous missions since 2000, and this rocket's just humbling for me. 430,000 miles per hour. The closest that came to that was Pluto New Horizons. When it left here, it was going 32,000 miles per hour, give or take. So quite a difference. And the next fastest, I believe, is going 150, 175,000 miles an hour now, which is one of the Mariner probes. So the speed is phenomenal. This vehicle is 233 feet tall. If you get a chance to go out there and see it, it's just, you have to see a human next to it to be able to capture how big this thing is. Like I said, I am from Launch Services Program. What we do is we contract with our partner ULA to build us a launch vehicle and provide us a launch service. We partner with the 45th Space Range and many other partners here and downrange from here to make this mission happen. So I am going to show you a film, if you could, of what it takes to build this rocket starting about a year ago when it arrived here, not built the rocket, but arrived here and assembled it. This is two of the segments arriving. There's three of these of the common booster cores. They're going to Complex 37 where they'll be bolted together. Here's the process. All three will be bolted together. The second stage is on front. That will be erected. That happened in April of this year, along with Parker arriving on April 1st, Easter Day. It's just mind-boggling how big that really is. Here's Parker Solar Probe inside of the fairing, and within there is the third stage. This is it being erected about 10 days ago and being put on top of the second stage and bolted down. So about a week or beginning of this week, we had our flight readiness review. That's where we get a bunch of mucky mucks together and we talk about what's gone on with the launch vehicle technically, how the range is doing. Kathy Winters, our launch weather officer, provides us a synopsis of how the weather instrumentation's doing and what she can give us as far as a forecast at that point. The range tells us how their assets are coming together, and the spacecraft tells us how they're doing and what their readiness is. We turned that around into a mission dress rehearsal, which occurred yesterday. We get the whole team together and we practice the launch countdown, and that was successfully run. We successfully stressed the team, and we're quite ready for what we got ahead of us on Saturday. This morning we had our launch readiness review. That went splendidly. We're successfully complete. We're not working any issues. The next step for us is rolling the tower back, which will occur tomorrow about 6 in the afternoon. About 10 o'clock at night, we'll get a weather brief, and that'll allow our folks to decide whether we're going to load the vehicle with cryogenics. That'll start at about 10:45. It's about a 3.5-hour process. I'll do my last poll roughly at 8 minutes, and at 2 minutes, I'll give them my final go for the government, and we should be launching at 3:33 in the morning. We have a 65-minute window. If we have to go to the following day, it becomes a 3:29 in the morning launch, again, 65-minute window, and that's kind of like, it gets a little bit earlier every day. And that's all I have.
Thank you so much. We're going to talk a little bit more about that Delta IV Heavy. Up next, we have Scott Messer, who can join us. He is the program manager for NASA programs for the United Launch Alliance. We're looking forward to this. Tell us about it.
Thank you very much. And on behalf of the men and women of United Launch Alliance, I want to welcome you to the Parker Solar Probe launch. This is a very, very exciting mission. Every time I hear Nicky and Andy talk, I get more and more excited about this mission. So, as mentioned, we'll be launching on a Delta IV Heavy, which is a 5-meter vehicle in size. Omar mentioned it's about 233 feet tall. When it takes off, the thrust of just the first stage, or the 3 cores, if you will, is about 2.1 million pounds. So we've heard a lot about speed today. United Launch Alliance has launched 6 other missions successfully this year so far, and since our inception, we've had 129 consecutive successful launches. So if you spent 60 years in the making for a mission and 4 million hours getting the spacecraft ready, you'd like to get the most reliable launch vehicle that you can to get there, and that's what NASA's done by getting the Delta IV Heavy. So the Heavy can lift about 14,000 pounds to geosynchronous orbit. And on the other hand, Parker Solar Probe weighs 1,400 pounds. So it's a little bit lighter, and so you might ask, why such a large vehicle if you've only got such a small spacecraft? And the answer we've heard is speed. All right, this thing goes like nothing ever has gone before, and it is super fast. And in fact, you'd be interested to know, Omar mentioned we also have on top of our Delta IV Heavy a third stage developed by Northrop Grumman. And if you look at the velocity that the vehicle provides compared to the third stage actually provides 2/3 of the speed that the vehicle, the spacecraft is going at separation. And that's because you need all that big giant vehicle to get out of the Earth's gravitational pull and to get up there. And so once we get there, then the third stage only fires for about an hour, about a minute and a half. It's very short, but it imparts a lot of velocity to that third stage, and our Northrop Grumman partners have done a great job in developing that. So with that, let's take a look at the video. I'll kind of show you the sequence of events that will happen on launch day.
5, 4, we have main engine ignition, 2, 1, and liftoff. Liftoff of the United Launch Alliance Delta IV Heavy rocket.
3 Delta IV RS-68A main engines ignite and generate more than 2.1 million pounds of thrust to lift the rocket away from the pad. Shortly after liftoff, Delta IV begins a pitchover to attain the proper flight path while minimizing the pressure the vehicle experiences during flight. The Delta IV reaches Mach 1, the speed of sound, at 1 minute 18 seconds. At 3 minutes 56 seconds, the port and starboard booster engine shut down. 2 seconds later, the boosters are jettisoned. The center booster engine then throttles to full power to maximize performance. Approaching main engine cutoff, Delta IV is burning propellant at a rate of 1,945 pounds per second, traveling at more than 15,381 miles per hour and located 86 miles in altitude and 415 miles downrange. At 5 minutes 36 seconds, propellant levels deplete and the main engine shuts down. 7 seconds later, the Delta IV separation system activates to release the first stage. The vehicle now weighs a little more than 5% of what it did at liftoff. At 5 minutes 55 seconds, the first Delta cryogenic second stage, or DCSS main engine burn, begins. During ascent, the spacecraft is protected inside a 5-meter diameter payload fairing. At approximately 6 minutes 5 seconds, the payload fairing is jettisoned. At 10 minutes 37 seconds, cutoff of the DCSS engine, or MECO-1, occurs. The mission now enters a nearly 12-minute coast phase. At 22 minutes 25 seconds, the DCSS main engine is restarted for the second burn. Approximately 14 minutes later, second cutoff of the DCSS main engine occurs. Following a 30-second coast phase, the third stage is separated to continue carrying Parker's Solar Probe spacecraft on its interplanetary trajectory. 20 seconds later, after the third stage has reached a minimum distance of 50 feet from the DCSS, the third stage is ignited. Approximately 1 minute 29 seconds later, burnout of the third stage solid rocket motor occurs. At 43 minutes 10 seconds, the third stage releases NASA's Parker Solar Probe spacecraft on its journey to the Sun.
So those are the events that will occur on Saturday morning. You got a little bit of a view as you looked at the Parker Solar Probe spacecraft and the big 5-meter size vehicle that you saw there. So NASA chose the Delta IV Heavy because of its unique capabilities to create the speed. The last time, I think Omar or somebody mentioned, the last time NASA flew on the Delta IV Heavy was the EFT-1 mission back in 2014. This will be the 9th launch of or the 10th launch of the Delta IV Heavy. The Delta IV Heavy first launched in 2004, so almost 14 years ago, and only 10 launches. So you can see we don't, the Heavy is not something we launch all that often. So it's a very exciting for us as well as the spacecraft. And as mentioned earlier, United Launch Alliance, we pride ourselves on making sure that our customers get all of their requirements met and are fully successful in getting it there. So we want to say thank you once again to all of our mission partners and to NASA for allowing us to participate in this very exciting mission. And I'll just close with a go Delta, go Parker Solar Probe.
Thank you so much. So we've been hearing all about all the things we have done to prepare for this launch, but we have one last thing that needs to go right, and that is the weather. To tell us a little bit about that, we have Kathy Rice. She is the launch weather officer with the 45th Weather Squadron with the Air Force right here at Cape Canaveral.
Thank you. Thanks. I am super excited about this mission, and I'm really excited about the 3:33 a.m. launch time. Because in the summertime here in Florida, 3:33 p.m. is very bad, and 3:33 a.m. is very good. We do expect to see these afternoon thunderstorms each day, but as the day goes on and we get into the evening, they'll dissipate. And then we'll just have to watch out for anything that forms offshore. Sometimes at night, that air cools. The water's a little warmer than the air. You get a little warming of the air just above the water. You get some rising air, and you start getting some cumulus clouds. offshore. But that happens more over the Gulf Stream, so it's looking more on the favorable side for launch. We will be dealing with a little bit of thunderstorm activity around the time of the mobile service tower roll tomorrow evening, but it should be finishing around that time, so it's looking good as we get into that operation and then moving forward into the countdown. So again, we'll just be watching for some clouds that we get concerned about for triggered lightning threat. We can trigger a lightning strike with a launch. And so it's not just a thunderstorm we're concerned about. We're also concerned about towering cumulus clouds or the tops of thunderstorms we call anvil clouds that come off and spread. So there's more than just the risk of natural lightning. We also are concerned about triggered lightning. So let's go ahead and look at the satellite picture for today. You can see that we do have that west coast sea breeze making its way across. We're in a southwest flow pattern. What that means for us is our sea breeze forms and kind of gets pinned along the coast. The west coast sea breeze moves across and merges, and so we get a lot of thunderstorm activity in the afternoons, particularly in the late afternoon in this type of pattern. We're expecting this to continue for the next several days. But the early morning hours are good in this type of pattern, so that's good for us. So let's go ahead and move into the launch forecast. You can see that we do have light winds. We're really not worried about winds because the pressure gradient's really light over the area. Temperature is always around the upper 70s to low 80s in the overnight hours here. And our only concerns will be offshore weather mostly, but anything coming within 10 nautical miles of us we'll be watching. So any cumulus clouds, any detached or attached anvil clouds, those clouds that come off of the top of the thunderstorms heading our direction. The winds in the upper levels will be from the east, and so we'll be watching that, just paying attention to that. With that, we have a 30% chance of violating launch weather constraints. So 70% chance go. Okay, and for our 24-hour forecast, we are looking a little bit worse. The relative humidity in the atmosphere gets a little higher. It gives us better chance for clouds in the area. So with that, I did increase the number to a 40% chance of violating launch constraints. And finally, if we happen to go one more day, it does get a lot drier, so I dropped the chance of just a 20% chance. But you can see each day the winds are light. It's really all about the clouds in the area and that triggered lightning threat. So overall, good launch time, so hopefully we have some good weather.
Thank you. If we can have the team come up for the Q&A here. And again, if you're joining us, we're coming to you live from the NASA Kennedy Space Center in Florida, a few days before the early morning launch of the Parker Solar Probe. And now we're going to go on the Q&A section here. And what better way, Karen, to celebrate the 60th anniversary to be here for the Solar Parker Probe, right? I mean, this is fantastic. So we're going to start again here with media, and please wait for the mic and give your name and affiliation. We'll go to social media and the phone bridge, and then we will wrap it up. So, right here.
Stephen Young with Astronomy Now and Spaceflight Now for Omar. We've seen lots of different launch times. They keep changing. Normally with a planetary mission, we think that these things are written in stone. Is there a reason why the launch times are so fluid with this mission? And then I have a follow-up.
So, it's on, okay. So there had been some, with the shifts in the days, the delays since the opening of the window, there had been some shifts. We started this with a 2-hour window. And as we looked at the trajectory, we realized that we are coming close to the Van Allen belts as we fly out. So we have a radiation concern on the launch vehicle as we fly near the Van Allen belts, which we have to stay away from because it could mess with our electronics, and we don't want that to happen on the way up. And so you'll see the window cut off at 65 minutes. We had been playing with different analysis to see what was the better option. So I wasn't firm on how large our window was. I would say about from anywhere from 45 minutes to 65. We're now at 65. There's opportunities later in the window where it expands to about 70 minutes. But after that point, the risk of seeing an upset on the way up increases dramatically. The very beginning of the window had some constraints early on with the spacecraft being able to be picked up by a station in South Africa, Hartbeespoort. And so there was a risk trade that had to be made as to whether that station was needed, along with another station that's further downrange that could see the spacecraft on its initial separation. So that's why there was a shift. Okay?
The final last-minute problems you had getting out of Astrotech and on the way to the launch pad, could you just address those issues and how you resolved them?
Sure.
And also how you got a couple of extra days at the end of the launch opportunity.
Okay, so let me address the, we had 2 delays on the way out. First, we were dealing with a very sensitive instrument purge that keeps the instruments on the spacecraft purged with nitrogen to keep any of the environment away from it, moisture, dust, whatever it may be that we have here that these instruments don't like to see, and you want to maintain them in pristine condition when you go out to do the science. So we did have some problems with some leaks in that purge as it threads its way up through the adapter cone through the 3rd stage. And so that cost us a couple of days. After we were done with that, we did have an issue where we damaged an electrical connector that we had to separate the stage again, or the fairing, to get at this connector, repair it, and get it back together. And finally, we had some issue with a minor weather stripping foam is the best analogy I can give you that you would use around the home that has adhesive on one side. Well, that foam started to liberate itself from the sides of the fairing. So we had to separate the fairing again, clean off all that foam, account for all those pieces, and make those stages back together. So that cost us, as you know, we started this on the 30th, we took a delay to the 4th, then we took a delay to the 6th, and we took a delay finally to the 11th. That's where we're at now. How we were able to get the additional 4 days, that had been in the works for quite some time. From the launch vehicle perspective, we actually had that in work over a year ago to add those additional days. The spacecraft hadn't had a chance to add those days, so that came in very late for us. That's why we expanded it from the 19th to the 23rd, fairly late for the public's knowledge, until the spacecraft was able to go analyze and plan for those days. And that's how we had those additional 4 days. But that is the cliff.
Okay, before we go to social, you have the mic, so real quick question.
It's quick. Sawyer Rosenstein with Talking Space. Question about that upper 3rd stage. So I know that's not very common with these science missions. So what exactly is the planned parking orbit for the Delta IV's 1st and 2nd stage? And then how much extra speed is that 3rd stage going to give in miles per hour or something like that?
You want to give it a shot, Scott?
So what I can tell you as far as the speed is that our requirement is a measurement of the velocity called C3. And the 1st and 2nd stage of the Delta IV get us to a C3 of about 50, 52, and the 3rd stage then takes us from 50 to 152. So like I said, about 2/3 of the actual velocity after we get out of the Earth's atmosphere. The other stages will be, so the 2nd stage and the 3rd stage, they're on a course to leave the atmosphere, so they just go, and there's no parking stage with those. And the cores will fall back down into the ocean.
Great, so now we will take a question over here from the social media side.
Jack, is this on? Is this on now? Okay. Jack Sauter with YouTube. Is there any contingency plan in case the 3rd stage doesn't ignite, or is the likelihood so low that you'll just get there if you get there?
So there is no contingency plan because like most of the stuff in the rocket, it has to work the first time. We're not something that can upload a command like sometimes you hear the spacecraft do if they have a problem. Everything has to work the first time. So we go through a very rigorous test program to make sure that we have the maximum probability that everything is going to work as appropriate. The engine that we use on the third stage is an engine that's flown many times. The Star 48 motor has flown hundreds and hundreds of times, and ignition has always been successful. So we just have to go through the process of testing and designing and testing and designing and testing and to make sure that we have the maximum probability that everything is going to work.
All right, we still have time for a few more questions, but we're getting close to the end of the show. I want to make sure we get in a question from the users who wrote in with Ask NASA as their hashtag.
A Twitter user named Brady asked, how long did it take to develop the technology to survive the simultaneous fusions occurring in the sun?
That's the.
I think that's a spacecraft.
Andy, do you want to?
You repeat the question?
Yes. A user by the name of Brady on Twitter asked, how long did it take to develop the technology that will survive the simultaneous fusions occurring in the sun?
Well, fusion is what powers the sun, so that's deep down in the heart of the sun. We're going close, but we're not going that close. So at 4 million miles off the surface, the temperatures are about 2 to 3 million degrees Fahrenheit. The spacecraft flies through that plasma. The plasma is very rarefied. It's not very dense, so the spacecraft doesn't pick up a lot of heat from that environment.
Okay, thank you.
One last question from our social here, and then we'll wrap up.
All right,
We
anybody
good?
else over here?
Anyone?
Oh. Thank you.
This might also be for the science team, but I know Parker Solar Probe has a lot of scientific instruments, but then there's like Juno, which has JunoCam for public outreach. Will Parker Solar Probe have anything like that?
So no, we only carry exactly what we need for the science. As we noted, we have to be incredibly light, even, we don't carry anything extra. And so our instruments are there to do the job that they are meant to do. We do have a white light imager, and we will be providing you with the first ever look at the sun's corona. So there is no sort of add-on camera on there. We are doing all science with our instruments 24/7.
Let's give a nice round of applause for our launch team here. Thank you all.
So you can stay part of the conversation going to our Twitter handle at NASA Sun and using the hashtag SolarProbe. And of course, we expect everybody to be watching this live on nasa.gov/live at 3 a.m. That's coverage starts.
Yeah. Launch coverage starts at 3 a.m. Eastern. Please look out for updates. And before we close the show, just a reminder, we have a fantastic contingent of scientists, principal investigators, engineers, and technical folks to answer your questions for the folks on the phone bridge and watching live on TV. They'll be at the press site, and then call the press site. There are plenty of incredible folks that can give you interviews, and there's a lot of excitement and buzz. So we're going to conclude here today. Lots of excitement. www.nasa.gov/Parker, right? And I think we're ready to sign off.
We just got one last countdown for you.
Right?
Ready?
So, we guys ready? 3, 2, 1. Go, Parker Solar Probe! Thank you all. See you at launch on Saturday.
From NASA's Kennedy Space Center in Florida, you're watching live coverage of the Parker Solar Probe mission to unlock mysteries of the sun's atmosphere. Good morning. I'm NASA's Marie Lewis. Thanks for waking up early this Sunday morning for our second launch attempt. We have team coverage of today's launch from NASA's Torrey McClendon at a viewing area near the iconic Vehicle Assembly Building, NASA Edge's Franklin Fitzgerald and Blair Allen, and NASA's Josh Finch and Mick Waltman at the Mission Director Center. We'll have in-depth interviews on everything you need to know about Parker Solar Probe and how the weather is shaping up. But first, Parker Solar Probe is targeted to launch at 3:31 this morning, Eastern Time, from Launch Complex 37 at Cape Canaveral Air Force Station. The launch window is 65 minutes long. Parker will take off on a United Launch Alliance Delta IV Heavy rocket, speeding up to 430,000 miles per hour in orbit. That's fast enough to get from Philadelphia to Washington, D.C. in just 1 second. It will travel 7 times closer to the sun than any spacecraft before. Parker will help us understand how the sun affects weather in space. So why is this space weather important? First, a little background. Parker Solar Probe is named after Dr. Eugene Parker, a physicist who figured out 60 years ago that our star actually has its own wind and storms, and they can spread far into space. This space weather can disrupt communication signals from our satellites and even cause power outages on Earth. Besides impacts here on the ground, we also need to understand solar wind to help us explore deeper into space. Just as ocean explorers need to understand currents, NASA needs to understand space weather to help us send astronauts to the Moon, Mars, and other distant destinations. Scientists have sought answers about space weather for more than 60 years and will send Parker into temperatures of 2,500 degrees Fahrenheit to find them. Coming up, we'll find out how Parker will manage to get so close to our star without burning up. But first, we are now about 28 minutes from launch, so let's check in with NASA's Josh Finch and Mick Waltman in Kennedy's Mission Director Center for an update. Hi, guys.
Good morning, Marie. I'm Joshua Finch, and I'm here with Mick Waltman. Good morning, Mick.
Good morning, Josh. I'm happy to be here on behalf of NASA's Launch Services Program.
And we're happy to have you. This is our second launch attempt for NASA's Parker Solar Probe on the Delta IV. Can you tell us a little bit about yesterday, why we scrubbed, and what happened right after that?
Yeah, absolutely. A lot of work's gone on by the launch team since yesterday's launch attempt. They've been working on a few things. The gaseous helium bottle pressure limit that resulted in yesterday's morning scrub was evaluated by United Launch Alliance and the NASA launch teams for today's op. The teams will continue to monitor that limit. However, they did place in some new limits for the port and starboard common booster cores, so they'll continue to watch that today. After detanking yesterday, the team did perform inspections of the launch vehicle bond-on-foam insulation, or BOFI. Due to the cold temperatures achieved during cryogenic tanking yesterday, minor repairs were required in some of the interface areas. They made those repairs, verified them this morning. They're ready to support today's launch tanking operations, and then we began with moving the MST earlier today to get ready for a launch early this morning.
And you can see that MST, or Mobile Service Tower, standing behind the Delta IV Heavy rocket on the screen. The teams also just received a weather briefing from the U.S. Air Force 45th Space Wing. The launch weather officer for today's mission is looking into a whole host of weather-related details, such as wind speed, cloud coverage, and more. And launch teams need to know this before committing to launch. That report came back pretty great. Our probability of violation is now just 5%. That means we are 95% go. Winds 6 knots out of the southwest. The temperature is at about 78 degrees. Those concerns that we were initially looking at with the anvil clouds, it doesn't look like any of them are going to drift into the launch area today, so we are really good on cloud coverage for today. So a good news story with the weather improving for us. And Mick, can you tell us a little bit about the Delta IV Heavy with the additional third stage that we're seeing on our screen now?
Yeah, absolutely, Josh. Due to the extremely high energy required for this mission, the Delta IV Heavy launch vehicle was chosen by United Launch Alliance and NASA LSP. The launch vehicle is unique in the fact that it has 3 first-stage hydrogen-fueled common booster cores. Each have an RS-68A main engine to provide the initial thrust out of Earth's atmosphere. On top of the center common booster core, you have a Delta cryogenic second stage with an RL-10B engine, which is used to achieve an intermediate escape orbit once in space. On top of that, we have a 63-foot, 5-meter bisector composite fairing, which protects Parker Solar Probe as it ascends through Earth's atmosphere on its way to space. And inside the fairing, along with the Parker Solar Probe spacecraft, we have a third stage provided by Northrop Grumman Innovation Systems, a solid rocket motor that is called the Star 48BV. It's a vectorable motor that's used to put that final push to send Parker Solar Probe on its trajectory to the sun. All of these vehicle features play an important role in getting Parker Solar Probe on its way to touch the sun this morning.
And again, a live shot there of the Delta IV Heavy rocket with the additional third stage at Space Launch Complex 37. And Mick, we've been sitting here in the Mission Director Center listening into the launch teams. Can you give me an update on what's happened so far in today's countdown?
Yeah, so far the teams have proceeded through the launch count. Launch conductor Scott Barney has orchestrated all launch steps with the launch teams to get the cryogenic loading done on first stage and second stage. The teams have finished that off and are maintaining and topping the stages currently right now.
So a lot going on here as we move toward a liftoff at 3:31 a.m. We are inside of a built-in hold at the moment, but we'll continue to monitor the countdown here at the Mission Director Center. But for now, we'll go back to Marie for more on NASA's Parker Solar Probe.
All right, thanks, guys. Parker Solar Probe will travel very far, very fast to get closer to the sun than any spacecraft before. NASA's Jessica Londa helps put it in perspective.
Launch of Parker Solar Probe is just the first step. Let's talk about what it's going to do on its own in space. Did you know our models for predicting what our star is going to do are incomplete? We can't fully understand the sun's physics if we've never been there. Here's how Parker plans to change the game. First, it's going to get up close and personal, flying just 4 million miles away from the sun's surface. And that may not sound so close to you, but if we put Earth and the sun on either side of a football field, Parker is going to tuck and run all the way to the 4-yard line, where temperatures can reach 1,000,000 degrees Fahrenheit. But don't worry, Parker's equipped to handle those kinds of temperatures, and it will use just a single gallon of ordinary water to do it. If you can believe it, the spacecraft's thermal regulation system is designed to collect and dissipate heat just like a car radiator. That way, we can stay where the action is, orbiting the sun's corona in order to figure out why it's even hotter than the surface itself. But the corona isn't just harmful to our probe, it's dangerous for us as well. That's because of a little something called the solar wind, discovered by none other than our spacecraft's namesake, heliophysicist Eugene Parker. The solar wind spews harmful solar particles way beyond Pluto, and no one knows exactly what accelerates it so far, so fast. That's why Parker is designed to hang out near the origin of this wind, so we can finally figure out what it's doing and what it could potentially do to Earth.
Thanks, Jessica. Data collected by Parker Solar Probe will provide an unprecedented picture of the sun. NASA Edge's Franklin Fitzgerald is live on set right now with senior heliophysicist Eric Christian. Hi, Franklin.
Hi, Marie. Now, Eric, you're the deputy principal investigator for the ESA suite of instruments on Parker Solar Probe. Tell us what those instruments are going to be used for.
So the ESA instruments study solar energetic particles, the highest energy particles coming from the sun. These are pieces of atoms that are moving at up to half the speed of light. And they're important. They're one of the 3 science questions for Parker Solar Probe. These are the particles that can actually damage spacecraft and even be a danger to astronauts.
Now, you said there's one of the questions that Parker Solar Probe is going to be looking at. What are the other 2?
So the other 2 questions are, why is the corona hotter than the surface of the sun? That seems really weird. Normally when you get further from a fire, you get colder. The corona is millions of degrees, whereas the surface of the sun is only thousands of degrees. How that happens, we're going to go to where the action is and figure that out. The third question is, how is the solar wind, this stream of particles that the sun blows out in all directions all the time, how is that accelerated up to 1,000,000 miles an hour? Again, from Earth, we can't figure that out. It's all been smeared out 93 million miles away. By going close to the sun, we can be where it's happening and actually measure
why the solar wind is being accelerated.
And actually, Parker Solar Probe is actually going to be looking at the origin of space weather, where the solar winds and the space weather begins.
That's right. So we're trying to do some basic science that'll be able to get us to the point where we can do models that predict space weather, which is what our eventual goal is. On the Earth, terrestrial weather, they're doing much better now on predictions, and that's because they have these really complicated atmospheric models, but they needed to do some basic science on how winds affected winds at other altitudes, how hurricanes move, and all that basic science was needed before they could do the models. We're doing the basic science for space weather models.
Eric, thank you for your help this evening, and I'm sure you're going to go find a spot to see the launch this evening.
I'm really excited about it.
All right. Marie, back to you.
All right, thanks, Franklin. Let's check in now with Josh and Mick in the Mission Director Center for an update and a closer look at the Delta IV Heavy, one of the world's most powerful rockets. Guys?
Thank you, Marie, and welcome back to the Mission Director Center. It takes a team to be able to launch the Delta IV Heavy this evening. Teams from NASA, United Launch Alliance, the U.S. Air Force, and more. Mick, can you characterize the teamwork that goes into doing something like this tonight?
Yes, Josh, as you said, it's a team effort to get a mission this far prepared for launch. Mission teams working around the country have prepared the rocket and the spacecraft for this morning's launch attempt. Teams from United Launch Alliance stationed in Denver, Colorado, from their production and manufacturing facility in Decatur, Alabama. We have spacecraft from NASA's Goddard Space Flight Center in Greenbelt, Maryland, Johns Hopkins Applied Physics Lab in Laurel, Maryland, and of course right here in Florida, the team worked on the spacecraft at Astrotech in Titusville, and here at Cape Canaveral Air Force Station inside the Mission Director Center at Hangar AE and the Delta Operations Center.
And that's a live shot inside the Delta Operations Center that we just saw there, where the NASA launch manager Omar Baez and the launch director Lou Mangieri from United Launch Alliance are working with teams toward a liftoff today of the Delta IV Heavy. Earlier in the countdown, the team received a weather briefing from the Air Force, which improved the weather forecast to 95% go, only a 5% probability of violation. But the U.S. Air Force not only briefs the launch teams of weather which could impact a launch, but they also keep the launch teams aware of other launch considerations on the Eastern Range, including telemetry coverage for public safety. And they update the teams on COLAs. Mick, can you talk about COLAs?
Yeah, your reference to COLAs, or Collision Avoidance Analysis, which is performed by the United States Air Force for public safety and the rocket safety, actually. One of the considerations they analyze is objects in space. For example, other satellites around the Earth that could be in the flight path of the Delta IV Heavy this morning. With a 65-minute window today, there could be some small cutouts, what we refer to, where the launch teams would not be able to lift off. This analysis is started days out. The final report is provided to the launch manager, Omar Baez, on the day of launch to help determine today's T0 for the launch attempt. We've heard there's no COLA cutouts for today's launch attempt, so we're still on schedule for a 3:31 a.m. launch.
And we do have an hour and 5-minute window should launch teams need more time, but we're at the beginning of the window right now. You're looking at live shots of the Delta IV Heavy rocket. And Mick, can you tell us a little bit more about what's happened up to this point?
Yeah, right now we're in the T-4 and holding. We've got about 12 and a half minutes left in this built-in hold. Teams have been working to get cryogenic tanking completed. Those operations are finishing up with topping and maintaining continuing. Things are progressing towards that 3:31 a.m. liftoff, as I mentioned before. We do have that 65-minute or hour and 5-minute window that you had talked about for tonight's launch attempt in case something does come up. But right now, all things are go and looking good for a on-time liftoff at 3:31 a.m.
So a lot going on here in the Mission Director Center, and we'll keep listening in to the launch teams as they prepare for liftoff. But for now, we'll go back to Marie.
All right, thank you, gentlemen. NASA's Tori McClendon is standing by live at one of our launch viewing areas with one of NASA's senior leaders, Dr. Thomas Zurbuchen. Tori?
Thanks, Marie. Dr. Zurbuchen, as head of NASA's Science Mission Directorate, help us understand why this mission was selected and why we need to study our sun.
Wow, this mission has been a long time coming. You know, that for 60 years we tried to do this mission, and it was selected finally because we had a mission that actually is feasible and viable. So we had the technologies to protect the spacecraft from the heat. And we had a mission that was fitting into our budget. So we're ready to go with this Parker Solar Probe.
So talking about going back 60 years, this is the first time ever that NASA has named a spacecraft after a living person, Dr. Eugene Parker. Can you talk about that decision?
Oh, yes. I was so excited to be able to call him and tell him, hey, can we name a spacecraft after you? And he's like, yes, that would be fine. You know, it's the only name that really fits there. First of all, he is the guy who came up with solar wind as a theoretical concept before it was found and observed in space. It's also true that his theories are really at the heart of 35 of our missions, of our 107 missions in science. And so it's just an incredible impact he's had. So his name belongs there.
Well, talk about NASA's Living with a Star program and how this mission fits into that.
Living with a star is an important part of heliophysics overall. So the mission, of course, does fundamental science. It looks at the atmosphere of our star, and with it, the atmosphere of stars everywhere. This is our Rosetta Stone. Our sun is our Rosetta Stone. Well, it's also our star in a sense that it's the source of space weather. And Living with a Star, of course, is focused very much on understanding space weather, really what the impact is of these emissions on our technological societies, the systems in space and on the ground that are affected by these perturbations that are coming down.
Well, we're definitely looking forward to the launch this morning, and you'll be watching with Dr. Parker himself, I hear.
Absolutely. I look forward to being right there with him, and I want to look at him when this rocket goes up there.
Great. Well, with that, I think we'll go back to you, Marie.
All right, thank you. Parker Solar Probe will set off to soak up the sun in about 14 minutes, but it's already had quite the journey. Here's a look at the months of work that led to this moment. For those of you just joining us, you're looking at a live view of Parker Solar Probe poised on the launch pad, ready to lift off in just about 12 minutes on a journey to kiss the sun and unlock its mysteries. I'm NASA's Marie Lewis. Parker Solar Probe is targeted to launch at 3:31 this morning Eastern Time from Launch Complex 37 at Cape Canaveral Air Force Station in Florida. The launch window will be open for 65 minutes. Parker will take off on a United Launch Alliance Delta IV Heavy rocket, speeding up to 430,000 miles per hour in orbit. That's fast enough to get from Philadelphia to Washington, D.C. in just 1 second. It will travel 7 times closer to the sun than any spacecraft before. Parker will help us understand how the sun affects weather in space. And that space weather is important. First, a little background why. Parker Solar Probe is named after Dr. Eugene Parker, a physicist who figured out 60 years ago that our star actually has its own wind and storms, and they can spread far into space. This space weather can disrupt communication signals from our satellites and even cause power outages on Earth. Besides impacts here on the ground, we also need to understand solar wind to help us explore deeper into space. Just as ocean explorers need to understand currents, NASA needs to understand space weather to help us send astronauts to the moon, Mars, and other distant destinations. Scientists have sought answers about space weather for more than 60 years and will send Parker into temperatures of 2,500 degrees Fahrenheit to find them. We are now about 10 minutes from liftoff, so let's go over to the Mission Director Center for an update from United Launch Alliance, and then Josh will take us through the count. Josh?
Thank you, Marie, and I'm being joined by Alyssa Macbeth of United Launch Alliance. Good morning, Alyssa.
Good morning.
Thank you for being with us.
Yeah.
We first have a video of the Delta IV and animation of it taking off and what's going to happen at T-0. If we could roll the video.
2, 1, and liftoff. Liftoff of the United Launch Alliance Delta IV Heavy rocket.
3 Delta IV RS-68A main engines ignite and generate more than 2.1 million pounds of thrust to lift the rocket away from the pad. The Delta IV reaches Mach 1, the speed of sound, at 1 minute 18 seconds. At 3 minutes 56 seconds, the port and starboard booster engines shut down. 2 seconds later, the boosters are jettisoned. At 5 minutes 36 seconds, propellant levels deplete and the main engine shuts down. 7 seconds later, the Delta IV separation system activates to release the first stage. At 5 minutes 55 seconds, the first Delta cryogenic second stage, or DCSS main engine burn, begins. At approximately 6 minutes 5 seconds, the payload fairing is jettisoned. At 10 minutes 37 seconds, cutoff of the DCSS engine, or MECO-1, occurs. At 22 minutes 25 seconds, the DCSS main engine is restarted for the second burn. Approximately 14 minutes later, second cutoff of the DCSS main engine occurs. Following a 30-second coast phase, the third stage is separated. 20 seconds later, the third stage is ignited. Approximately 1 minute 29 seconds later, burnout of the third stage solid rocket motor occurs. At 43 minutes 10 seconds, the third stage releases NASA's Parker Solar Probe spacecraft on its journey to the Sun.
Alyssa, a lot happens after T0, but can you tell me what's happened up to this point and what's about to happen in the count?
Yeah, so the rocket is ready to go at this point. It's fueled. The people on console all their systems have been checked out and are ready to go, and we're about to enter into a terminal count poll conducted by the launch conductor, where the launch conductor will poll each engineer and verify that their systems are in fact ready with a simple go, and that indicates that the launch is ready and Delta's ready to fly.
And we're just about 18 seconds away from that poll. Live on your screen, you can see the Delta IV Heavy rocket with the additional third stage at Space Launch Complex 37 on Cape Canaveral Air Force Station, and we'll listen in to this poll in about 5 seconds.
Status check to proceed with terminal count. First stage systems, propulsion. Go. Hydraulics. Go. Locks. Go. LH2. Go. Second stage systems, locks. Go. LH2. Go. Third stage systems, third stage vehicle manager. Go. Electrical systems, airborne. Go. Ground. Go. Facility. Go. RFFTS. Go. Flight control. Go. COM. Go. GCQ. Go. Operations support. Go. Pneumatics. Go. Umbilicals. Go. HAZGAS. Go. ECS. Go. Redline monitor. Go. Quality. Go. Op safety manager. Go. ULA safety officer. Go. Vehicle system engineer. Go. Anomaly chief. Go. Range coordinator. Clear to proceed. Launch director. You have permission to launch. Proceeding with the count. MEQ established swing arm lock pins pulled. Active.
And we just heard the poll with all stations reporting that they're go for launch. Alyssa, we're entering the final few minutes of the count here, about 5 minutes and 45 seconds before we launch. And can you tell me what it means to United Launch Alliance to be able to launch the Parker Solar Probe mission?
Yeah, ULA is always excited about doing interplanetary missions. The chance to get to explore the solar system is something that we look forward to and are happy to be a part of. This mission means a lot to us. It is a Delta Heavy, so Delta Heavy gets to show off its performance and get Parker Solar Probe exactly where it needs to go, which is the only rocket currently that can do that. So we're excited to be a part of that. Yeah.
Well, thank you very much for being with us, and enjoy the launch today.
Thank you. You as well.
Thank you.
L minus 5 minutes. OVM, transfer third stage to internal power. Roger. All steps are complete prior to terminal count.
And we have about 30 seconds remaining in our hold in the T-minus clock. After that, the L-minus and the T-minus clocks will be synced up. You're looking at a live shot of the Delta IV Heavy rocket poised for liftoff from Space Launch Complex 37 at Cape Canaveral Air Force Station. And we'll pick up the count. 5, 4, 3, 2, 1.
T minus 4 minutes and counting. Minus 355. Ground pyros enabled.
And once again, we're about 3 minutes and 20 seconds before liftoff. And Mick, can you tell me what we have left to go in the next 3 minutes?
Yeah, the teams are securing LOX and LH2, liquid hydrogen tanking there. They'll be finishing that up, getting ready to go internal. You'll hear a call for spacecraft power to internal. They'll be arming their flight termination systems and getting ready for launch, and then bringing the Delta IV Heavy launch vehicle onto internal power to prepare for the final terminal count.
Minus 249.
And we are coming up very shortly on the verification of the spacecraft being on internal.
CBC locks at flight pressure and flight level.
Minus 230. NSC, verify spacecraft on internal power.
Verified.
And we are at T-minus 2 minutes, 5 seconds, and counting. After liftoff, we'll be listening to the voice of United Launch Alliance, Patrick Moore, providing ascent commentary.
155. Launch sequencer start. Minus 140. SCS launch enable. 137.
CBC LH2 at flight pressure and flight level.
FTS armed. Minus 120.
We'll see you armed.
FCS count started. T-minus 1 minute.
Engine start box go.
Rock, report range status.
Range green.
50.
LCOVM. Third
Go,
stage is
OVM.
go for launch.
Roger.
Range green. Second stage LH2 secure at flight level.
40. Minus 30. Status check. Go Delta. Go PSP. Minus 15. Roll for ignition. 10, 9,
Nine,
Pisser start.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
3RS-68s look good in the full thrust mode. Five seconds into flight. Chamber pressures continue to look good on all three boosters. Now 35 seconds in. Chamber pressure on the core booster is throttling down to the partial thrust mode. Response looks good. Now 50 seconds into flight. Strap-on boosters look good in the full thrust mode. Core booster looks good in the partial thrust mode. Now 1 minute into flight. Vehicle trajectory looking good right down the middle of the range track. 1 minute, 10 seconds into flight. Coming up on 1 minute, 19 seconds into flight, max Q, maximum dynamic pressure, and Mach 1, Delta IV is now supersonic. One minute, 30 seconds into flight. Port and starboard booster engines continue to look good in the full thrust mode. Core booster looks good in the partial thrust mode. One minute, 45 seconds into flight. Trajectory continuing to look good right down the middle of the range track. ACS press valve has been opened. ACS pressure response looks good. Two minutes, 10 seconds in. Strap-on boosters continue to look good in the full thrust mode. Core booster looks good in the partial thrust mode. And Delta IV has gone to closed loop guidance. Two minutes, 30 seconds into flight. And at 2 minutes, 39 seconds into flight, the Delta IV rocket now weighs just 1/2 of what it did at launch, burning propellant at a rate of almost 5,000 pounds per second. And launch vehicle is now 33 miles in altitude, 49 miles downrange distance, traveling at 4,500 miles per hour. 3 minutes into flight. RS-68A engines in the port and starboard boosters continue to look good in the full thrust mode. Core booster looks good in the partial thrust mode. 3 minutes, 15 seconds into flight. Trajectory continuing to look good down the middle of the range track. Approximately 2 minutes remaining in the boost phase of flight. Chamber pressures continuing to look good on all three boosters. Port and starboard booster in the full thrust mode, core booster continuing in the partial thrust mode. And standing by for a strap-on booster throttle down momentarily. Port and starboard boosters have begun to throttle down. And we have jettison of both strap-on boosters. Core booster is throttled back up to full thrust. Response looks good. Four minutes, 25 seconds into flight. Upper stage lock system has begun boost phase chill down sequence. And 1 minute remaining in boost phase of flight. And upper stage fuel system has begun boost phase chill down. Five minutes into flight. Just over 30 seconds now remaining in first stage phase of flight. Core booster engine continues to look good in the full thrust mode. Vehicle trajectory continuing down the middle of the range track. 5 minutes, 20 seconds into flight. And standing by for core booster throttle down momentarily. Core booster has begun to throttle down. Standing by for BECO. And we have BECO booster engine cutoff, standing by for stage sep. And we have good indication of stage separation. NED is deploying. We have pre-start on the RL-10. And we have ignition on the RL-10 engine. Engine chamber pressure looks good. And we have good indication of payload fairing jettison. Now 6 minutes, 20 seconds into flight. And with the boost phase of flight complete, Parker Solar Probe will now continue its journey to the Sun. And it's 6 minutes, 50 seconds into flight. RL-10 chamber pressure looks good. Seeing good responses on the upper stage RCS system. And after a brief review of booster performance, seeing very close to nominal performance on the booster. And this first burn of the second stage will last approximately 4 minutes, 42 seconds. Now 7 minutes, 30 seconds into flight. About 3 minutes remaining in the first burn. And at 8 minutes, 30 seconds into flight, RL-10 chamber pressure continues to look good. Seeing very stable values on the upper stage LOX and LH2 tanks. ACS storage bottle pressure looks good. And vehicle body rates are very smooth. Now 9 minutes into flight. And at 9 minutes 40 seconds into flight, just under 1 minute remaining now in the first burn of the second stage. Second stage continuing to perform nominally. Carlton engine performing well. Tank pressures look good. Vehicle body rates remain smooth. Ten minutes into flight. And about 30 seconds remaining in the first burn. And standing by for MECO 1 momentarily. And we have MECO. Body rate smoothing out nicely. And now seeing upper stage ACS firings as expected. Now 11 minutes into flight. And this will be approximately a 13-minute coast duration prior to MES 2.
From the Mission Director Center, I'm joined once again by Alyssa Macbeth of United Launch Alliance. For those of you that are watching, we had an on-time liftoff today of the Delta IV Heavy rocket. And Alyssa, can you tell me how the launch went?
Oh my goodness, that was a beautiful launch. Just the sound and everything. Oh, it was great. It's looking good so far too. We saw good separation of the boosters from the main core and the booster from the second stage. Just experienced MECO 1. There's going to be 2 burns of the second stage, so that's coming up. The second burn, second engine start. And then in just approximately 45 minutes, we'll see payload separation. So everything's looking good so far.
Great. And can you tell me a little bit about your experience working with ULA and what it's like to work in a mission like this again?
Yeah. So I get to work with the innards of the rocket, the electronics, the avionics boxes, ordnance, pyrotechnics, all that kind of stuff. So working on a mission like this is something really special. To be able to get your hands on a vehicle like this and do something that's going to affect the world is really, really amazing.
Well, thank you very much again for being with us, and I think we'll talk to you a little bit later in the broadcast.
Mm-hmm.
Thank you, Alyssa.
Sounds good. Thanks.
And at 13 minutes into flight, Delta IV upper stage is continuing the coast period prior to MES 2. Vehicle systems all performing nominally during this coast, seeing periodic thruster firings as expected. Tank pressures and body rates remain stable. And a brief review of the performance from the first burn, seeing fairly close correlation on major orbital elements. Performance appears to be pretty good.
From the Mission Director Center, once again, we had an on-time liftoff of the Delta IV Heavy rocket. On your screen, you were seeing a live telemetry view animation of the rocket on its flight path. So things are looking pretty good at this moment as we're in a coast phase right now. And we'll go back to Marie Lewis for more on NASA's Parker Solar Probe. Marie?
All right, thanks, Josh. And I don't know about you, but here in the studio, we could feel the rocket rumble. And I know for our folks here on the TV side, that never gets old. We have Tori standing by now with a very special guest. We've been talking about him the whole show. And Tori, we can't wait to meet him. Please introduce us.
Thanks, Marie. I do certainly have a very special guest with me, Dr. Eugene Parker himself. Dr. Parker, you just watched the launch of the mission that bears your name. What was that like?
Well, I really have to turn from biting my nails and getting it launched to thinking about all the interesting things which I don't know yet, and which will be made clear, I assume, over the next 5 or 6 or 7 years. It's a whole new phase, and it's going to be fascinating throughout. I'm anticipating that the results will turn up basic information on why the corona of the sun is at 1 million degrees. That accounts for the acceleration of the solar wind. I'm just waiting for the data now, and the experts can get busy and sort it out, because there's an awful lot of data coming in, or will be a lot of data coming in. All I can say is, wow, here we go. We're in for some learning over the next several years.
That's right. So we'll definitely be anxiously awaiting that data and research. I also hear that this is the very first launch that you were able to witness with your own eyes. Is that right?
That's right. The video, of course, has supplied all of us with views of rocket launches, but somehow when you're looking at the real thing, it's quite impressive.
Nothing compares to the real thing, I would think.
Yeah, it's a little like the Taj Mahal. We've all seen pictures of the building and what a graceful structure it is, but if you happen to be in India and stop by that way, there's the real thing, and video and paintings and so forth just don't catch it somehow. Your mind is in a different state when you're looking at the real thing.
Well, we are certainly all honored to have you here with us this morning. Thank you so much for joining us.
My pleasure.
Marie, we'll go back to you.
All right, thanks, Tori. So great to have him here on the show. Understanding the sun will give us valuable information for future space missions. Mike Riskovich from Johns Hopkins Applied Physics Laboratory is live on set now with NASA Edge's Blair Allen. Blair?
Thanks so much, Marie. Listen, I got to tell you, I'm very excited, but I want to know, did you get out and see the launch, witness it firsthand?
Oh, yeah, I'm really excited. I had to run outside, and it was an absolutely beautiful night. The shock waves rolling over you, the beautiful sight of those 3 boosters rolling in. We could see it a long way. We could actually see the burnout, which was at about T+4 minutes, so really exciting night.
Now, what you work with primarily at the Applied Physics Laboratory is space exploration. How does a mission like this, we know the valuable science that it's going to get, but how does this help other missions with regard to space exploration?
Well, this is going to be a really big deal, not just for space exploration, but people on Earth. We're going to get a lot of new knowledge, which is going to help predictions and warnings of severe solar events that can take down the power grid or other pieces of our technological society. And then as we go ever more further into space, robotically or human, it's important to be able to get better forecasts and warnings for the operators of the robotic spacecraft and the people that go there. Today we're kind of like the mariners were in a few hundred years ago, where you didn't get warnings of hurricanes, and we want to be able to provide those warnings so we can keep people and hardware safe.
Yeah, exactly. Keeping our hardware safe, and all those future missions we have, and even some of our current missions will be able to help them as well.
Yes, no doubt. We try to design to withstand the harshest environment, but it's always worthwhile to have a good warning and know when you got to hunker down and play things safe until the storm blows over, so to speak.
Yeah, exactly. Well, I appreciate it. Thanks so much for coming off console to be with us for a few minutes and answer some questions. We look forward to getting great things from Parker Solar Probe.
Thanks. We look forward to it, too. We got a starting line and a finish line. Finish line for the development team and the launch team, and the starting line for the science team for 7 years of discovery. So,
awesome.
Thanks.
Yep. Back to you, Marie.
All right. Thanks, Blair. So how do we get close enough to the sun to actually sample its incredibly hot atmosphere? It's complicated, but NASA's Tori McClendon caught up with Dr. Nicky Fox, project scientist for this mission, to help illustrate Parker's path.
Thanks, Marie. Nikki, thank you for being here. You're welcome. So there's so many fascinating things about this mission. One thing that I find particularly interesting is the unusual orbit that Parker's going to take once it launches. Can you explain that?
Yes, once we're in space, it's a very busy first couple of weeks for us. We have to get it commissioned and all ready to go because just 6 weeks after launch, we encounter the planet Venus for the first time. We use Venus to give us a little gravity assist. Basically, it's like a little handbrake turn and it focuses our orbit in towards the sun because we don't want to be dragged around in any way or influenced by the Earth's orbit. And so during our 24 orbits of our 7-year mission, we actually will do these flybys of Venus another 6 times. And each time, as you can see from this animation, our orbit is getting smaller and smaller until those final 3 orbits, we are at our final closest approach.
Speaking of closest approach, can you describe exactly how close the Parker Solar Probe spacecraft is going to get to the sun?
Yes, at our closest approach, we will be 3.83 million miles above the sun's surface. And I realize that you just thought, million? That doesn't sound very close. Right. But you know, the Earth and the sun are 93 million miles apart. And so if I put the Earth and the sun in the end zones of a football field, Parker Solar Probe would tuck and run all the way to the sun's 4-yard line, well in the red zone, knocking on the door for a touchdown, right by that goal line.
Well, that sounds extremely close to me. So I'm sure that folks are now wondering, how is a spacecraft not going to burn up at the 4-yard line?
We have a wonderful heat shield that we keep oriented between us and the sun. And so it keeps everything in the main body of the spacecraft nice and cool. It kind of creates a shadow. And it has a white coating on it that was specially designed for Parker Solar Probe, very much like you prefer to be in a white car on a hot day instead of a black car on a hot day. The heat shield is glowing and it is reflecting a lot of the sun's energy. And so the front side of the heat shield gets to about 2,500 degrees Fahrenheit, but everything on the main body in that shadow is at about 85 degrees Fahrenheit. So much like a pleasant Florida evening.
That sounds so lovely. Well, Nikki, thank you so much for being here today. We're all extremely excited about this mission, Go Parker Solar Probe. And with that, Marie, we'll go back to you.
We are coming up on another major milestone in Parker Solar Probe's flight. Let's head back over to Josh for the latest. Josh?
Thank you, Marie. I'm here again with Alyssa Macbeth, and we've been monitoring the flight as it's gone so far. And can you tell us a little about where we are now and what's about to come up next?
Yeah, so as I mentioned earlier, there was two burns of the second stage. So we're about to come up on that second burn. After that, the engines will light and we'll enter that phase, and then they'll cut off and we'll enter into a coast phase right before second stage separation. Then the third stage will ignite at approximately 37 minutes into the flight, and that will be our last and final burn before spacecraft separation.
So we had a great launch on time this morning at 3:31 a.m., but there's still more work to do.
There is.
Before the spacecraft separates.
Mm-hmm.
And can you tell me what's next for United Launch Alliance?
Yeah, our team is still working they're monitoring data in the launch control room and in Denver as well as here, just looking to make sure everything looks nominal, that the booster performed. They're probably looking at data from the booster and making sure everything looked clear and good there. And as we continue through the flight, they'll continue to do that.
Well, once again, you're looking at a live telemetry feed here. It's an animated feed that you see of the second stage. When at the very top of it, you see NASA's Parker Solar Probe there, which is moving toward its separation time. And we just have confirmation of ignition of the RL-10 engine. And with that, Alyssa, thank you for joining us today, and thank you for a great launch.
Thanks for having me again.
Yes.
Thanks.
Body rates continuing to look good, chamber pressure remaining stable. 24 minutes, 5 seconds into flight.
We are at a mission elapsed time of 24 minutes, 50 seconds into launch. The second burn of the RL-10 engine you see on your screen from the telemetry feed that is updated in real time. We'll continue to monitor things as we move toward spacecraft separation, where Parker Solar Probe will then begin to unfurl its solar wings. But for now, we'll go back to Marie Lewis in the studio. Marie?
All right, thanks, Josh. The Parker Solar Probe mission is designed to collect data and study solar processes that scientists have never seen before. NASA Edge's Blair Allen spoke with mission system engineer Jim Kinnison about the unique challenges in developing this mission.
Jim, tell me, what is the Parker Solar Probe mission?
So since the beginning of NASA even, there's been a desire to explore the regions around the sun, close into the sun, to understand the processes that are going on there, how the particles coming from the sun are accelerated, how all of that energy goes out into the solar system and even to the Earth and beyond. Parker Solar Probe mission is the final fulfillment of that vision. We'll be able to fly the spacecraft into very close regions of the sun, make those fundamental measurements by taking this approximately 10-foot long spacecraft with a nice heat shield on the front and keep it pointed in the sun to protect all of those things that allow us to make those measurements.
Why has it taken so long to get a mission like this together? Because I know this is all new technology.
So there have been some fundamental technologies that we've had to develop over the years, and there have been many people working for decades really to get those technologies in place. Some of those are things like the heat shield. Some of it is also in the area of developing the systems we need to control the spacecraft we're in those regions. Parker Solar Probe is a very autonomous system. It has to maintain itself without a lot of help from humans. So the ability to do that in space is really one of those fundamental technologies we've had to develop. We've also had to develop things like cooling systems for solar arrays so that we can power the spacecraft when we're close to the sun and maintain those temperatures that allow us to continue to make the measurements.
Couldn't you just use one really small solar panel for right when you get close and get all the energy you need?
So surprisingly enough, we actually do that. When we get close to the sun, we actually take those solar panels and tuck them behind the shadow of the heat shield until only the very tips of the solar array are generating power. So it's essentially that idea, yes.
I should have been an engineer.
Exactly.
Anyway, that's really awesome. Now, I understand we're going close to the sun, but you're not just flying to the sun. How is this mission oriented to get to the sun and get those measurements?
You're absolutely right. It's actually a fairly complicated process to get there. We'll be launching at a very large rocket to give us a lot of delta V that allows us to take out a lot of the Earth's angular momentum so that we can sort of fall into the sun, but that doesn't get us there. We actually have to do a flyby of the planet Venus and use our gravity assist to take more angular momentum out of the system so that now we can make that first approach around the sun. We'll continue to make several more Venus flybys, and every time we do that, our perihelion, the closest approach to the sun, will get closer and closer to that point where we finally are seeing the science that we want to see.
So how long is the Parker Solar Probe mission?
It's about 7 years to get the final set of data that we want to get. We'll be making 24 passes close to the sun in those 7 years, starting out at about 6 months for each orbit, and then down to about 3 months per orbit by the time we get to the end of the mission.
What happens after 7 years? I mean, are you going to get pulled into the sun, or could you operate beyond that if possible? Or
we will likely at some point run out of propellant, and propellant is the thing that allows us to correct for momentum and to point the spacecraft. Once we run out of propellant, the spacecraft will actually start rotating just because of the natural forces around the sun and the pressure of the sunlight on the spacecraft itself. And surfaces of the spacecraft which are not supposed to see the sun will see the sun eventually, and so that will have all sorts of effects that we don't really understand, and eventually the spacecraft will join the dust cloud around the sun.
See, that's why I asked the question, because Captain Kirk went around the sun and they actually went back in time. So I was just trying to find out if there was some extracurricular mission op that might send you back 7 years so you can get 7 more years of data.
He had the advantage of having warp drive. We don't have that.
Well, you know, something to put into development.
That's right.
Josh is standing by with a representative now from Northrop Grumman who has a big role in this mission. Josh?
Thank you, Marie. And we're sitting here continuing to monitor the burn that we have here before main engine cutoff 2, which is approximately about 8 minutes and 30 seconds away for the burn of that engine. And now I'm joined by Katie Nieves from Northrop Grumman. Katie, can you tell me a little bit about yourself and what you do at Northrop?
Sure. I'm a project manager for the Space Launch Program, supporting this Parker Solar Probe team.
And can you tell me what Northrop Grumman's role is with this launch?
Northrop Grumman Innovation Systems and sector and the divisions within it have really supported this mission tip to tail. Starting with the large composite structures, basically everything white on the vehicle, the nozzles, the fuel tanks, and certainly what I'm most familiar with, the third stage.
And right now you are looking at a live shot there. That's live telemetry that we're getting. The second stage engine continuing to burn, but after that, the third stage, the stages will separate, and then we'll have third stage ignition. And can you tell me what is unique about this mission for Northrop Grumman?
Sure. Every mission has its own personality and challenges to overcome. This mission in particular, the sun, gives a new element. So there's a couple things to keep to take into consideration. The vehicle's trajectory is going very close to the Van Allen belt, and so the engineers had to create some rad tolerant electronics mass, keeping the vehicle as light as possible so that it could have the most performance is certainly a goal. And then I'm also told that this is the first third stage on a Delta IV Heavy. So those are definitely some unique aspects of this mission.
And so can you tell me a little bit more about this specially designed third stage?
Sure. Overall, it's about 7.5 feet long, and it weighs approximately 5,200 pounds. But it includes a Star 48 BV solid rocket motor. It includes flight avionics that's built on our heritage designs, which includes an onboard flight computer with navigation, adapter structures, and its own separation systems.
And so we're still continuing to monitor the burn of the second stage here, approximately 6 minutes left in that burn, and continue to talk about the upper stage. Has Northrop Grumman developed upper stages for missions before?
We have. Most recently, with the Star 48 BV in 2013, Northrop adapted our Minotaur 4 vehicle. We added an upper stage to create a Minotaur 5 configuration for the Laddie mission that that went to the moon. And just last year, we had another Minotaur 4 out at the Cape on ORS 5 that was a uniquely designed upper stage for to perform a required plane change.
And once again, you're looking at a live telemetry feed of the spacecraft flying over the South Africa near the heart of V-Stock, which is the HBK that you see on the bottom right of your screen. And so after this burn completes, we have a couple of events that are happening pretty quickly. Can you tell me about third stage ignition, how long this burn is going to last?
Yes, the Star 48 BV motor burns for about 1.5 minutes, and it produces over 15,000 pounds of thrust, which is about 20% of the total velocity of this mission, and about 60% of the overall orbital escape energy.
Has the Star 48 flown before?
It has, most recently on the Laddie mission in 2013, and then also our TACSAT 4 mission earlier in 2011.
And we just have about 4 minutes, 20 seconds left in this burn. And Katie, can you talk a little bit more about how Northrop Grumman has partnered with United Launch Alliance for this mission?
Northrop and ULA have a long-standing relationship that we're very proud of, and it's got different roles depending on the mission. Sometimes we're a customer, as in the Cygnus mission to the International Space Station. Sometimes we're a vendor, as in the large composite structures that we have provided for this Delta IV Heavy mission. And in this case, we're very proud to be a partner with ULA and NASA.
We have about 3 minutes, 35 seconds left in this burn of the RL-10 on the second stage. We had an on-time liftoff at 3:31 a.m. Eastern of the Delta IV Heavy rocket with the additional third stage that we're speaking about now. The second stage continues to fly in its planned trajectory.
And about 3 minutes remaining in the burn. RL10 chamber pressure continues to look good. Second stage fuel and oxidizer tank pressures remain stable. ACS press bottle also looks good. Now passing 35 minutes into flight. And at 35 minutes, 35 seconds into flight, approximately 2 minutes remaining until MECO 2. At MECO 2, the second stage will send a discrete command to the third stage to begin the initialization sequence. At that point, we should expect to start seeing telemetry data from the third stage through their transmitter. 20 seconds after separation of the second and third stage, the third stage will ignite, and it will begin its 89-second burn. Approximately 1 minute remaining until MECO 2. And standing by for MECO momentarily. And we have MECO, main engine cutoff. Now passing 38 minutes into flight. Third stage transmitter is on.
And visual cue there of separation.
Third stage telemetry. And we have acquisition of third stage telemetry. And we did see ignition on the third stage, seeing chamber pressures, seeing some periodic dropouts of telemetry. Now 39 minutes, 30 seconds into flight. Should be expecting to see third stage burnout momentarily. Apologize, we're still seeing some periodic dropouts of third stage telemetry, difficult to make calls. And at 40 minutes, 40 seconds into flight, still seeing some telemetry dropouts from the third stage. At this point, the third stage would have completed the burn and would be turning to the spacecraft separation burn attitude on a nominal timeline. Still looking for some data to confirm that. Delta flight commentary at 41 minutes, 56 seconds into flight. We are still experiencing some dropout of third stage telemetry. I'm trying to confirm that the sequence of events, and we'll provide updates when that's available. Now passing 43 minutes into flight. And per a nominal timeline for today's mission, should be expecting to see spacecraft separation in approximately 1 minute. And we've been informed that the third stage is providing data to a ground station. Do not have real-time data, so we will provide updates of those events as they come in from a playback. At 44 minutes, 30 seconds into flight, still attempting to confirm occurrence of events for the third stage phase of flight. And per a nominal timeline, should have expected to see spacecraft separation within the last minute.
And you're looking at a live shot there, the Delta Operations Center. Team shaking hands. Teams in the Delta Operations Center shaking hands. Now the United Launch Alliance Mission Control Room. We have had confirmation of spacecraft separation.
Attention on Net 2, would like to confirm the spacecraft has acquired data, and we are working on a playback to get our third stage confirmation. But at this point, spacecraft is up and happy.
And confirmation of spacecraft separation there. You're looking at a live view inside the Johns Hopkins Applied Physics Laboratory where teams were just celebrating. And I'm still joined here by Katie Nieves of Northrop Grumman. And Katie, can you tell me what's next for Northrop Grumman?
Well, congratulations to the entire team. Best of luck for Parker Solar Probe. Coming up in the fall, we've got the Pegasus Icon mission right here in the Cape. We've got the Antares launch in November out of Wallops Island, Virginia. And then next year in April, we've got the Ascent booster test here also at the Cape, April of 2019.
Well, thank you very much for being with us tonight, and enjoy the rest of your day.
Okay, thank you for having me.
And once again, you're looking at a live view inside the Johns Hopkins Applied Physics Laboratory. We've just had confirmation of spacecraft separation, so the teams were pretty cheerful, pretty joyful in the room there. We did have an on-time liftoff of the Delta IV Heavy with the additional third stage this morning at 3:31 a.m. Eastern Time. But for now, we'll go back to Marie Lewis in the studio. Marie?
All right, thanks, Josh. In order to collect data for this mission, Parker Solar Probe is outfitted with several sophisticated instrument suites. NASA Edge's Franklin Fitzgerald spoke with project scientist Nicky Fox about the diversity of data researchers will study.
You're going to be collecting a lot of science data with Parker Solar Probe. Tell us about the instruments you're going to use to collect that information.
So we have a wonderful payload that was very carefully thought about and put together to make sure that we could make all of the measurements that we really need to do to answer these groundbreaking science questions. So we have 4 instrument suites. We have a white light imager, which we call WHISPER, that is going to look around the side and take images of the solar wind that is about to impact the spacecraft. And so it's really going to help us kind of unlock all our other measurements. We have the fields suite that is going to measure all of the electric and the magnetic fields that very cold. Now, if you think of taking any material and heating it and cooling it many times, say 24, which is the number of orbits that we have, most of the time it will change its property. It will either become elastic or it'll become brittle, but it won't be the same 24 times later. All of our materials have to be the same. And so finding materials that would actually be able to withstand these changes was, of course, a challenge. And then testing them. The Parker Solar Probe spacecraft will be seeing just less than about 500 times the amount of sun we see here at Earth. So 500 suns in the sky is what Parker Solar Probe will be experiencing. And so how do you test it? We actually had to build test facilities just to be able to do this. We used reconditioned IMAX projectors because it turned out that the light that they put out is very much like sunlight. And so every single thing about this mission is challenging.
Well, can I go back to the IMAX projectors? What does that look like? How many projectors? What kind of facility do you construct this projector field to do this test?
So the original plan for this particular instrument was to use a solar furnace simulator in France. The problem there was that it only works during the day, and it only works if it's not cloudy. And so we couldn't get long runs to be able to get continuous hours and hours and hours worth of data. And so they actually constructed their own test facility. So up at the Smithsonian Astrophysics Observatory in Boston, they actually constructed basically a vacuum chamber, and then they took the 6 IMAX projectors and sort of chained them together, and so that would provide the right amount of illumination with the right amount of scattering angle for the light, the heat, and also firing particles at the same time to be able to really simulate what that instrument is going to see when we get very close to the sun.
Is there an opportunity for Parker Solar Probe to collect any science on its way to Venus and back to the sun?
So our intention is to have the instruments on it as much as possible. So we will have them on for the full journey in around the sun and the full journey out. The only time that we will not have the instruments on really is if we're doing a major maneuver on the spacecraft, or if we're sending our data down when we need all the power to go into the system that is going to transmit the data. And so we switch off the instruments during those periods. I often get asked, are you going to do science around Venus? And unfortunately, my quick answer is always no, because whenever we are flying past Venus, that is our prime time to get our coronal science data down. And so the instruments are planned to be off when we do our Venus flybys. There is one later in the mission. We actually do 7 of them. There is one when the instruments can be on, and we are excited about what kind of science we'll be able to do then. But that's a number of years away, and few days away from launch. Everybody's focusing on the launch right now.
Where are you going to be for launch?
For the launch itself,
yes.
I will be honestly as close as physically possible to the Delta IV Heavy, but in reality, I will be somewhere around the press building, probably looking through my fingers at the site of the Delta IV Heavy. But actually, if they let me light it, I would.
I'm sure you would.
It's taken us 60 years to get through technological advances that will get us ready to launch Parker Solar Probe to the sun, as you saw a little bit earlier. And here's why it won't melt as it flies through the sun's corona.
NASA's Parker Solar Probe is a mission to explore the sun. How can it do that? Why won't the spacecraft melt? Excellent questions. You can't face off with the sun without packing the right gear. This is why Solar Probe is equipped with a white shield that reflects heat off the front and keeps things cool in the back.
The heat shield is made out of a couple of different materials. One is carbon-carbon, which is a lot like the graphite epoxy you might see in your golf clubs or your tennis racket, but it's just been superheated. The inside is a carbon foam, which is just another form of carbon and is actually about 97% air. It's a very lightweight way of making a very strong structure.
Nobody likes a needy explorer. Solar Probe can take care of itself, thank you very much. And that's because it has autonomy software that will keep its instruments safe and cool behind the heat shield.
We're too far away to joystick it into place, so it basically has to always be sensing whether or not the heat shield is in the right position and correct itself if it isn't. There are these things called solar limb sensors that are just poking out at the very edge of the shadow, and if those get illuminated, the spacecraft knows, oh, I'm going the wrong direction, and can actually right itself.
It's important to stay hydrated in the sun, even for a spacecraft. Solar Probe circulates water to keep the solar cells from overheating. It stays cool and keeps power.
So basically, water flows behind the solar rays and into the radiators, and so the water warms up when it's behind the solar cells, and then cools down up at the radiators, and so that heat transfer is happening a lot like the veins in your body.
Yes, you read right. Heat is not the same as temperature. Temperature is a measurement, but heat is energy transfer. This matters because Solar Probe will be visiting the sun's outer layer, the corona. Like all stars, the sun is made of plasma. How tightly packed that plasma is depends on the layer. While the sun's corona has a very high temperature, the plasma particles are fairly spread out. So even though the temperature in the corona is 2 to 3 million degrees Fahrenheit, the heat around the spacecraft is manageable.
The corona and where we're going is actually not that dense at all. There are only a couple particles. And so when we think about it, those are very hot, but we're not touching a lot of them. It's the kind of like when you put your hand into an oven, and the oven might be at 400 or 500 degrees Fahrenheit, but your hand isn't at 400 or 500 degrees Fahrenheit.
Thanks to its design and destination, this cool, confident spacecraft is all set to explore. We can just sit back and chill as Parker's Solar Probe takes the heat.
We are now approaching solar array deploy, or when Parker Solar Probe will spread its wings. Let's go back to Josh in the Mission Director Center to walk us through this next event. Josh?
Thank you, Marie, and we are at a mission elapsed time of about 58 minutes and 10 seconds, and as you mentioned, we are waiting for solar array deploy. That could happen as early as 12 minutes after spacecraft separation. That's a live shot. Everyone gathered around inside the Johns Hopkins Applied Physics Laboratory. We are standing by for an interview with NASA's launch manager, Omar Baez. He's going to talk more about this mission and how things went tonight. So we'll wait not only for solar array deploy, but also to hear from tonight's NASA launch manager. I am now being joined by the NASA launch manager, Omar Baez. Omar, can you tell us how the mission went tonight, how the count went?
So the count went splendid today. Very boring, which is awesome for this kind of launch. We had a tough day yesterday and weren't able to get off in the allotted time that we had. And today just went completely opposite of it. Very quiet all day, and virtually had no anomalies to work, and the weather cooperated with us, and it went off like clockwork.
Can you tell me the importance of the Parker Solar Probe mission to LSP, to the Launch Service Program?
So it's very important. It's been one of our most difficult and challenging missions to date. In our 20-year history, we've been through some challenging ones, and I think this one tops the list on the scale of technical challenges. This one's it. And I'm very proud of the team that worked to make this happen. And we made it happen with a very short window at the very end for us. On a vehicle, very powerful vehicle, flying a new avionics system. And it just phenomenal to see that Delta IV Heavy take off today. And we were as close as you can get to it as possible. The energy of that vehicle, the immense size, and when you realize just how tiny the Parker Solar Probe satellite is, and you have this big vehicle around it, it is just mind-boggling. It was really nice to hear Tori McClendon interview Dr. Parker, and he mentioned there are a couple of icons in the world, and one of them being the Taj Mahal. And until you see it up close, you can't believe how big and beautiful and for real that thing is. Well, I can say the same thing about the Delta IV Heavy. Until you see it, and you see it up close, you just can't believe it. And when you do, it's just a miracle of technology. And we at NASA and the Launch Services Program are thrilled to be part of this mission.
And it's been a busy year so far for NASA LSP. And can you tell us what you have coming up next?
So yeah, it's a very busy year. We started 6 missions this year inside of a short period of time. We do have 2 missions remaining this year. The ISAT mission on the very last Delta II out of Vandenberg Air Force Base, and we look forward to transitioning the team as soon as they get a night's rest over to Vandenberg so they could do a mission dress rehearsal, or a mission a crew cert, which is the tanking test of the Delta II this coming Wednesday in preparation for launch of the ISAT-2 mission on September 15.
Well, Omar, thank you very much for being with us tonight. It was a beautiful launch. And we did receive confirmation that the solar arrays had fully extended. So with that, Marie, we'll now go back to you in the studio. Thank you.
All right, thank you so much, Josh. This concludes our live coverage of the launch of Parker Solar Probe to learn the secrets of the sun's atmosphere and help protect our assets in space. For more information about the Parker Solar Probe mission, visit nasa.gov. I'm Marie Lewis. From all of us here at Kennedy Space Center, thank you for joining us this early Sunday morning. We will leave you now with replays of Parker's launch to touch the sun. Have a great day.
Roll for ignition.
10, 9,
8,
7, 6, 5, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
368 look good in the full thrust mode. 25 seconds into flight. Chamber pressures continue to look good on all 3 boosters.